Okay. Hello, good evening, all. I have not yet released the question. I would release them now. Uh, but let us do that after 1 more minute. I would do that at 2 minutes past 8.
Sure, sir.
Yeah.
Excuse me, sir.
Yeah.
Sir, I haven't gone through the videos, sir, for this week. Should I just attend the session or should I watch it later?
Ah, mm, you might attend. See, if you have something very important going on, then I think you can drop. I would try to discuss some concepts whenever I'm when I'm coding from scratch. But yeah, it would obviously help you if you watch the lectures first.
Okay, sir.
Okay, so I have published the three questions, and I have also given the link to the replet in the chat box. So yeah, you can just check the message box if you don't have the link. Fine. So we would be doing three questions in this session, and they are basically normal the linked list data structure and queue data structure, that kind of basic questions. Yeah. I hope you guys can see the problems, right?
Yes, sir.
Yes, sir.
Yeah, yeah, we can
Sir,
see
can
it.
you please release the questions on the portal also?
Portal, we would release it after this.
That will be, I think, after the deadline.
Yeah.
Okay, sir. Okay, sir.
So we would start discussing the first question at let's say at 8:15. Till that time you try. Okay.
Okay, sir.
Audio is there, sir?
Yeah, yeah.
Okay. Thank you.
No, Yogendra, the class has started. Since it's a live coding session, we are actually starting the discussion at 8:15 or let's say 8:17 most probably. Yeah. Till then, you all can try the code. Okay. At least the first code we would start discussing at 8:17. Yeah, Tilwan, you want to say something?
Hello, sir. Good
Hello.
evening.
Good evening.
Sir, in this first problem, we are asked to delete the elements from the queue,
Ah.
and we have to use a linked list. Is it a single linked list which is we are using here?
See, so obviously because
Simply,
this class definition has been given to you, right?
yeah, yes,
So
sir.
so it has only head pointer and the I mean head and tail, right? And in each of this node you can see the data is there and the next pointer is there.
Okay,
Next means only one arrow, I mean
only one.
one link you can have.
Yes. Mhm.
So it's a single link list.
Okay.
So what you have to do is basically write two functions over here. Like we have the traverse function, just like that you have to write the enqueue and dequeue function. This place.
Can you see my code, sir, Nikhil? Test cases are failing.
I would see the code. Let us wait for 2 more minutes. Okay.
Okay.
And basically, this is what we will do from now on in the live session, in the live coding sessions. That if someone is confident of a particular code, so then we can pick it up and see that how he has done it. And then if no one is confident, or yeah, you want some other, I mean, you want me to code along with it, so then I can code myself. That is also there. Okay. So it's better that you figure that out on your own where the problem is occurring, or because everyone we cannot tell every different implementation, right? You can always question in between. That
Okay,
would be better. Okay. You can always question why a particular, or let when you see the code, you would anyway understand that where the problem is
yes, sir.
occurring. Okay. Fine. Anyway, so let's start it. By the way, before starting this session, uh, can all of those who have seen week 3 lecture, can you all raise your hands? Okay, quite a few. Nice. So then I want to ask a few questions first before moving into this coding, which is, so we actually left our discussion last time comparing different sorting algorithm, and we compared insertion sort, selection sort, and merge sort. And we saw that merge sort was taking n log n time because it was breaking it up into two halves every time, and we derived it how it is taking n log n time. And all the other algorithm, in worst case it was taking order n squared time, but merge sort was taking worst case, best case, any case you give, merge sort will, because merge sort's way of solving the problem is not dependent on whether a particular number is, I mean, so it's not comparing each pair of element, right? It's sorting subparts and then combining or merging those subparts. That's why it's called merge sort. So that's why there is a merge sort is very case independent kind of sorting, because whether you give whatever may be the sequence of numbers, like in selection sort, if you give a different sequence of number, right? So the best case can be order of n. Sorry, in insertion sort, the best case can be order of n if it is already a sorted list, right? But in merge sort, irrespective of whether it is the best case or worst case, there is no best case or worst case for merge sort. All of these are same. Merge sort actually takes order n log n time, whatever input you give. So like in insertion sort, oppositely sorted array is the worst case, and the, I mean, properly sorted array, right? Suppose you want to do insertion sort on an insertion sort to sort the array into ascending, in the ascending sequence, and I am giving input an already sorted ascending sequence. So that's the best case for insertion sort, and that takes order n time. And the oppositely sorted array would take order n squared time. So it has two different distinct growth function or cases, that is your worst case and best case, but merge sort doesn't have any. It's always takes order n log n time. Okay, so that was one point. Now regarding quick sort, we saw that quick sort also has worst case and best case, just like any other sorting algorithm like insertion sort and all. And we saw that its worst case can grow up to order n squared time. And when basically we are pivoting always one of the terminal element, which is at the start or at the
Hello,
end.
sir.
Yeah, hello.
Hello. Sorry to interrupt you.
Yep.
Sir, in merge sort, what is the meaning of when we sort a list in a reverse order? I mean, what reverse order means here? What does it mean, basically?
No, not reverse order. What I meant to say is, suppose you give in insertion sort a list which is already sorted in the proper ascending order. So let's say your motive is to sort a list in ascending order. Okay, so you want to sort in ascending order. Now by using insertion sort, and and I give you as the input, I mean the input to the insertion sort on which the insertion sort would work, right? That list is sorted in ascending order. Okay, so
Sir,
you're
I'm talking about merge sort.
I'm coming to that.
Oh, sorry.
Yeah,
Okay.
so that would, since it is already sorted in ascending order, and I explained, I think, with examples why it takes order n time.
Hmm.
So insertion sort would take you order n time in its best case. Okay, and in worst, sorry, what do I do? Why did I write it like this? What I mean is insertion sort characteristics is its best case is order n. Okay, and worst case is order n square. Fine. But in merge sort, whatever may be the input you give, whether it is ascending, descending, sorted, unsorted, whatever may be the case, there is no separate worst case and best case for worst case and best case for insertions. I mean merge sort, like in insertion sort. So its omega is also n log n, and its order is also n log n. There is no difference, which basically
Okay.
means, which basically implies theta is n log n.
Hmm.
Fine. So there is no separate worst
Because-
case and best case for merge sort.
Theta is between O and omega. Okay, so only for merge sort, there is no
Only
such
for merge
case.
sort you can say that theta is n log n. For insertion sort and selection sort, there is a separate explanation for theta, and that's not in our discussion. That's not in our syllabus. Okay. It would lie somewhere between n and n square, obviously, but that depends on the c and n naught and some other technicalities are there. Doesn't matter. But basically, this is the scenario. So what I was telling is, so these are fine, but in quick short, what you
I
Yeah.
could not recollect what is theta is.
theta is average case. That is
Error
maybe yeah, average case. So you can check the session, that live session. Okay, I discussed there, or in the lectures you can see what it's basically the average case between the best and the worst case. So it lies in between.
Oh, average case.
So quick short, the best case for quick short is obviously n log n. But again, the worst case for quick short, the order term, it is n square. Okay, so we discussed quick short in this week's lecture. That's why I asked how many students have seen it. So quick short took order n square time, and this basically happened when we chose the pivot element, right? Pivot is one of the terminal elements. Terminal element all the time. All the time means quick short is also a recursive code, right? You write quick short by using recursion. So in all the recursive cases, if we pick the pivot element to be the one of the terminal elements, terminal elements means either the first element or the last element as pivot. So then you would land up in trouble. So that's when basically you're sorted. The whole time for quick short takes order of n squared time. And how the recurrence, can someone tell me what is the recurrence of quick short?
n by 2.
N by 2.
Tn by 2.
Quick short.
N.
Worst case quick short. Okay, sorry. Let me tell it.
Okay, worst case it will be n.
n log n.
n square.
N minus
N square.
N square fine. That's why that I've
n
already
minus
written.
1. P of n minus 1 will be.
Correct. Yeah.
Hmm.
P of n minus 1. Then
Plus
N
1.
minus 2. N minus 2.
Plus n, sorry.
plus
Plus n. Plus n.
N.
plus order of n, or you can write it as some constant times, and that doesn't matter. Why is this time taking? What is taking this time?
Because we went to check which elements are less than pivot and which are more than pivot. So to decide that for each element it takes order n.
Correct. So we place. So when I run the algorithm of quick short, this order n time is basically taking to, if I let's say take one of the pivot element and place it at this position. This is my pivot element. So all the element on the left hand side must be smaller than the pivot element, and all the element on the right hand side should be larger than the pivot element. So this algorithm, this task of placing the pivot at a position so that all the left elements are smaller and all the right elements are larger than the pivot P, this task takes order n time, right? This task is taking order n time.
And T of n minus 1 because of
Since the pivot is placed at
we
the
are,
last position. Yeah.
s-
So in this case, since I'm
Okay,
taking the
last
worst case, yeah. The idea of T of n minus 1 is, since every time we are placing the pivot, we need to make sure whatever is on left, it should be large, smaller, and on right, it's larger. In the case when we place the pivot at the terminal position every time. So basically this was your, let's say, on all the iterations, the pivot element is placed
Hmm.
at the last cell. So what that means is,
okay.
or whatever is on left hand side is the element which is lesser than pivot. That is correct. So from this, so after we run one recurrence of quick shot, right? So basically quick shot is a recursive code. So at every recursive step, what can I guarantee? I can guarantee, so let's say this is one step, some ith step, right? Ith recursion. What I can guarantee is everything on left of P, right, is
As lesser
than P. So that is
P.
fine. But the second thing that I can also, most of the time it would be happening, not most of the time, I mean, except one time it would always happen. That is this thing sorted? I told that left of P are smaller. So obviously if P is 100, so I must have elements which are lesser than 100 over here. But what my question is, are those elements sorted among themselves? Right?
No.
That's not the case, right? So
Okay,
this is
not no.
yeah. So these are not sorted elements. But so if I have P is 100, what I can guarantee is I can have any element from 1 to 99 over here, considering I'm only considering positive integers. So only 1 to 99 can be here. That I can guarantee. But I cannot guarantee it would be in the order of 1, 2, 3, 4 to 99. It can be 99, then 28, then 34 randomly. So that's what this algorithm is doing. It's placing the pivot elements at its proper position. But what does this mean? If I am always placing the pivot either at the last position, or same thing will also happen if I place it at the first position, the first cell. Okay, first cell of the list or last cell of the list. In either of these two cases, what is happening is this was your whole length of the list, right? N was the length. So N was the length.
So leaving the pivot, it will be n minus 1.
Right. So the whole length was N, and therefore my after this n order of algorithm ran, it divided my list into two halves, and in which one half is of a single element and the other unsorted part, right? Unsorted part is of n minus 1 length. What was merge sort doing? Merge sort was dividing into two sorted equal halves, right? It was dividing into two halves, and both of them were sorted among themselves. Yeah, both of them were sorted. So this is also sorted. This is also sorted. Our task was when I merge them, then I have to actually do the comparison, which was taking my m plus n minus 1 number of comparison at most. So that's the idea of merge sort. So, but basically it always sorted the total list into subparts of two sub list, and they were sorted. So that means if this was n, then every time merge sort would do n by 2. But here, if my pivot is always placed at one of the terminal position, every time it is doing what? N minus 1. It's not doing n by 2. But merge sort would have done. Right? So that's why this is T of n minus 1 plus constant time. Yeah.
Sir, in the merge sort, we do this merging and sorting in two snippets. Now, first we divide in two parts, and both parts are sorted. First we sort the two parts, left and right part. First we sort left part and right part, and then we merge. Is
Correct.
it so? Or,
correct.
Yeah. Right now, that means the two snippets. First sort and then merge.
We break them first, then we sort, and then we merge. Correct. Okay. So anyway, so basically quick short, this is the worst case scenario. But this might not always be the case if my pivot is placed somewhere in between, right? I mean, if my pivot element is placed somewhere in between, so then this is not n minus 1. What would happen is this would become something like
n by
so this would become your some n by alpha. Okay.
n by alpha.
Some n by some division, and then again you would have another
So
term.
can't it be 2?
Yeah,
instead
it
of
can
alpha?
obviously. Yeah. Alpha can be 2. That's it. Let me write a
Okay.
general equation. Let me write a
Okay,
general.
sir.
Okay, and n by alpha, n by 1 minus alpha. Yeah, fine. Plus.
Another why 1 minus alpha? Why it is because n by alpha and n by alpha.
No. If it might not be always. So if you break it down,
Okay.
if you break a list, this is a list, right? If you
Yeah,
break,
got it.
this is the division. So may I'm saying these are the 3 parts, right? So this is 1 by 3, 1 by 3, 1 by 3, and actually suppose my break happened over here. So this is the point where my partition, I mean this order and algorithm placed the
1
pivot.
minus 2 by 3.
So what would be 2 by 3 would be one part, this one, and
Hmm.
1 by 3 would be one part. So basically what? If you do 1 minus 1 by 3, you would get 2 by 3, or anyway, other way around also happens. So that's why this is the general equation.
Yeah.
Okay.
Okay. Anyways, so this is now if you want that, if it so happens that the pivot is placed in the center, which would have happened in case of merge sort. So this alpha would be 2. Right? I mean, a half, sorry.
Yeah,
N by
2.
yeah, so
No,
it
n
would,
by 2.
yeah, n
If
by
it is
2.
in the middle.
So then both of them would sum them up and it would be twice. So that was the point. Merge sort, quick sort, worst case, best case. But if I sum it up, I insertion sort, selection sort, merge sort, quick sort. Okay, these are the best case and worst case. Insertion sort best case was n, it was n square. Selection sort, whatever you do, it takes n square. Merge sort is best case is also n log n. Worst case is also n log n. Quick sort is n square, and best case is n log n. Is it n or is it n log n?
N log n.
Best
N log n.
Why it is not n? Because the partition algorithm, if you okay, so I don't think you're aware of this term. Okay, so while discussing quick sort now or in future, I might use the term partition algorithms. Many of you might be aware of it, but many of you might not be, because that's not the term used. So this algorithm, this constant C of n time algorithm, this one which I discussed, placing the pivot at a position so that all the elements left of it is smaller and right of it is larger. So this algorithm is actually, if you see the literature, it is called partition algorithm. Okay.
Sir, a partition algorithm means where we divide the list into 2 parts and check if elements to the right of the pivot are less than the pivot. And
yeah, that part, particularly that part where you place all the element, I mean, you place the pivot at the position where all the elements on the left of it is smaller and the right of it is larger. So that task, I mean, you choose the
partition.
pivot and then compare. You use I and j two variable, right? And you do, if ai is less than aj, then you simply ai plus plus. You do that thing, right? So that algorithm is partition algorithm. So yeah, so that is that order and task that you are doing. So why quickshot can never be order of n? The reason for that is in order to sort the list, you have to apply partition algorithm, that is that order and task. You have to do that multiple times in the recursion. Every recursion call is basically running that order and operation multiple times. But if you do once also, that also takes order and time. Partition algorithm takes order and time, right? Even if you want to do it once, it takes order and time. But in quickshot, you need to apply that multiple times. So that's why it is some multiple of order n, and that multiple is log. That is, you do in log n times that order n operation you do, which takes you n log n time. That's the idea. So it can never be order n time, because even if you do partition once, that takes order n time. Okay, so it must be some value greater than order n. That is order n log. Anyways, so this is how you can remember, but this is the list. Now, the whole point of me discussing this today is, can someone tell that what were the scenario under which these two algorithms were used? So I asked you that in which situation you would use insertion sort and in which situation you would use selection sort.
So when the memory is low.
Memory is low, fine then.
Sir, we would use insertion sort when existing list already sorted, sir.
So now this is the thing. You cannot say anything on the basis of the input. The reason for that is when you are writing an algorithm, you might be aware of what kind of data. So let me put it in a real life context. What I mean is, so you are writing an algorithm to sort the balance. I mean, whatever bank balance, suppose a bank has many accounts and it has bank balances, and you want to write a code to have a feature in the, let's say, in the bank's interface, which would sort the name of all those persons. I mean, it would present the name of all those persons in a sequence of having their bank balance maximum. So basically, you want to sort all the bank accounts which that bank has, right? All the bank accounts which that bank has in the increasing order of their in the decreasing order of their balance. That's what you want to do, right? So if you want to do that, you only have this much information. You don't have what is the amount of money in each bank account. That's a privileged information, right? That you as a programmer or you as a bank employee, you wouldn't have. I mean, the clients you are handling is fine, but you wouldn't have the information of all the persons whose account is there in the bank. But that's my point is, when you are writing a code, you don't have the input cases, and that's a fundamental idea which you all should have while we proceed through this course. That main problem is we don't know how the input would look like when we present it in real life. When you write a software, you don't know who would be using it and after how many years it would be used. So what would happen, what kind of input would be coming to it, that you don't know. What you definitely can gather is on what kind of data my particular system would work. So you don't have the exact data, you don't have the information of the input type, but you certainly can gather information about the metadata, or the what is the nature of my data. So if you say, when we would use a sorting algorithm when the list is sorted in some specific order, then that's not metadata. That's exactly, you are concluding about what is the data itself. But so what I would give you an example of what metadata. What do I mean by the word metadata? Metadata means information about data. Means data. Metadata means data about data.
Data
Okay.
about data.
Data about data, or information about data. So what that means is, so you all have done your maths and stat classes. So I think you all are aware of sparse matrices, right? So a sparse matrix is basically which has more zero entries compared to normal matrix. So when you are dealing with complete graphs, or let's say you are writing a code. I know we have not yet discussed graphs, but what I'm trying to put. By the way, you all have learned graph theory, right, in maths?
Yes.
But then then it's fine. Graph theory we have learned. Okay, so now just pictureize a situation where I am, let's say the task that Google Maps does. So you have roads and all in a real life city. So you would have so many connections of points and lots of things, right? I mean, there are so many streets and everything.
Yes.
So there are obviously considerable amount of edges in, if I represent the whole map of a city using nodes and vertices, nodes and edges. So then that would definitely have many number of considerable amount of edges. And if I want to draw the adjacency matrix, you all are aware of adjacency matrix? No, I think.
Yeah, it is covered in math one.
It is
Yeah, it is covered.
Great.
Previously, it was there in the graph theory. It was there in the, I think.
Okay, great.
Now
We will learn this time also, I think.
but still, that is confusing. Somehow.
Well, we would discuss anyway when we reach graph this week. So anyways, so if you draw the adjacency matrix, then it would have considerable amount of values. So it is never a sparse graph. So now when we go to graph week, we would discuss how you can decide what is better and which data structure is not. Okay, so we can leave it for now. But the basic idea is, that is the kind of information that you get. You don't know how many streets are there. You don't know what is the distance between the streets. But what you can certainly guess is, I would have a considerable amount of streets, and those streets are basically my representation for edges. So I would have a considerable amount of edges. Now with that information, you can decide what kind of program you want to write. So that is not the whole map. You are not getting the exact map, but you are getting information. There is considerable amount of roadways in the city, because it's a capital. Chennai is so let's say I'm talking about Chennai. Chennai is a 8-tier city. So it would have a lot of road networks and all. So maybe my graph would be somewhat congested. So that kind of information you can get. Okay, but if I say you go to some place which is very internal, some let's say tier 3 city, and that also let's say 30 kilometers away from a tier 3 city, so then that would have most probably one big road and channels moving out from that big road. So that's what most probably would be. So if you want to represent that as a graph, then there is a higher probability that you would have a lot of zero entries, because every in an adjacency matrix, because every road might not be connected to every other. Okay, and most of the times it wouldn't be connected to any other except one, the main backbone road which is there in the city. So then you can have a high chance of sparse matrices. So you don't have the exact map of the city, but you can have assumptions, or no, I would not say assumption. You can have information like this to decide how the ultimate data on which I would work would look like. That's what we call metadata, right? Data about data, or information about data. Now, when we write code, when we implement algorithm in real life in a software, we can have multiple metadata or information about the system on which our program might run, and information about the data on which my program will run, right? So when I say these are the two important factors, so we have two informations. First is the system information. System information, basically how much fast your hardware is, how much memory you can give me. Depending upon that, I would write a program, because if you give me less memory, less hardware capabilities, I have to settle down for less efficiency code, because I need more hardware in order to juice out more speed and more efficiency, right? And the second important thing is, what is the nature of my data? That is my metadata I was talking about, nature of data.
Sir, how you are referring that one set of data will have multiple different metadata? Can you please explain me that?
Metadata is just information about the data. So
it should be unique, no? It cannot be multiple sets, will not be there, no?
I didn't get what do you mean?
You said that for one given set of data,
Yeah,
there will be multiple metadata.
see, I am telling you one thing. So let's say you have a bank. I mean, you are writing code to do some stuff in the banking database. Fine. Now, what is the probability? How I give you 100, I tell you there are 100 accounts in the bank. Fine. And I don't tell you what is the balance is in each one of them. Okay. And if I ask you how many accounts would have zero balance, I mean, what is your chance? It's 100 accounts are there. You just go to a real life bank. This is not some hypothetical situation. Go to a real life bank, pick 100 accounts at random. Do not see what their balance is. And I'm asking you the question: how many banks would have? How many accounts among them would be zero? Obviously, it would be very, very less, right? Zero. Most probably, you wouldn't get a single account which would be zero. And even if it is, then you would have 2 or 3 accounts. So this is metadata. I never told you what is the balance in each one of them. Okay, but you can certainly guess that it wouldn't be zero, right? I mean, most of them wouldn't be zero. So that kind of, so that's what the idea of that city came in. I told you, if you have a big city on which you are writing a code, you don't have the exact representation of the city mapped into a graph structure. But what you can certainly guess is, if it's a 8-tier city, there would be a huge number of road network, and that's why my graph would very much resemble, not to a complete graph, but it would go somewhere 40 to 50% towards a complete graph, because there would be a lot of connectivity. So you don't have the exact graph, but you certainly have information about that graph, so which is your ultimate data. But when you come to a normal 3-tier city and some village area or something like that, it wouldn't have a lot of road networks. So obviously, if you represent it in an adjacency matrix, then it would be very much. There would be many zero entries. So it would resemble a sparse graph, sparse matrix. What I mean is, so these are, so you're knowing that I am going to work on a program which would be representing, which would be working on a city which is tier 3 city, or which is a tier 1 city. So this information is metadata. You going to the bank and obviously picking up data, provided that bank is not an agricultural or rural bank which government has sponsored for farmers, so that even with zero balance account they can run. If you know that thing, if you know that if I'm going to a bank which is a NABARD bank, NABARD is National Agriculture and Rural Board, I think, full form I forgot. Basically, these are banks sponsor or support farmers. So if you go to such a bank, the probability that you would have a many zero balance account is there. But if you go to a normal bank in a city, you hardly get a zero balance account. So the thing is, whether you are going to whether you are writing a code which would be working on, let's say, bank data, working in a city, or whether it is in a village where government sponsors scheme is running, right? So this kind of information, data or information about the original data on which you are working, that is metadata. And it might not be unique, obviously. I mean, whatever insights you can draw from the data, that is your metadata, right? So there can be multiple insights. There can be thousands of different insights. That is what metadata is. Metadata is just information, right? And by having that information, you can take judgment. So for example, in this case, what I was trying to explain is, in insertion sort and selection sort, I tell you that, okay, I don't know what the input would be, but I can certainly say, and this was the exact question I asked, if in a system, the number of swap operation takes more time, right? I tell you that we have a system in which the swap operation is taking more time. That's it. This is the information that you have. You don't know what would be the input. You don't know the data. I only told you that, okay, that's why I wrote it over here. We have 2 points to consider: nature of the data, not the data itself, nature of the data and the system information. On these 2 factors, we have to decide which algorithm we choose. And obviously, these factors are there. But as long as you are not beating some algorithm in all possible contexts, then you finally come to. So if there is a tie between 2 algorithms, then we come to this kind of information. So I tell you that if in a system the swap operation takes a lot of time, then the better one is selection sort, because selection sort does order of n swaps, but insertion sort in worst case would do order of n square swaps. Please visit the previous session if you have doubt in that. I discussed it over there. So depending upon that, you use selection sort. But certainly, if you do not have any constraint in the system where the swap operation performs bad, then it's better to go for insertion sort, because the best case of insertion sort is order n. So if I run insertion sort on a random list, let's say for 1 million times, there is a chance that at least a few times I would have the sorted list. And when it is already in the sorted order, that list, right, it would take order n time. But selection sort would anyway take order n squared time. Okay, so if I tell you there is no system constraint, then insertion sort makes sense, because it's good in this best case scenario. But if I tell you there is a system constraint and the constraint is swap operation is slow, so then insertion sort is bad. Then selection sort is good, even though it is taking n square. Why? Because the best case of occurrence, that every time the whole array would be already in sorted order, that is very less. But swap operation would anyway happen in both the algorithm every time they run. So if I can optimize the part of the code where it is which is occurring more frequently, then I would get a better efficiency. Fine. So in that case, selection sort is good. So these are the kind of reasoning that you have to do while actually writing real life softwares. And
so swap will be low when the memory is almost full, right?
Swap would be low when?
Swap is going to take more time.
Yeah.
When our computer is almost full of memory, like it's almost
no. I wouldn't say that. The main idea of selection sort was that it takes least number of swappings. Okay, so that's why we put the question in that format. So let's say in a system the number of swaps is less. I mean, basically swap operation, it doesn't work like that. It has nothing to do with memory.
I think you explained last time 1 + 2 + 3, right? I think
yeah. Fine. So these are the 2 points for insertion and selection sort. And now merge sort. Yeah.
There are lots of sorting algorithm there, right? Why only 4 and 5 algorithm would be needed?
No needed. You can learn as long as you want 1,000 of algorithm and implement them. There are multiple, and you can use any one of them. Doesn't matter. Even we would also learn one more sorting algorithm in the further week, right?
Okay.
These are the basic fundamentals. So insertion sort, selection sort, these are basic sorting algorithm. Quick sort, merge sort basically follow a divide and conquer approach. Now I told what is divide and conquer approach, although we would again we have a dedicated week for that, but still I mentioned what is divide and conquer in the merge sort lecture. Fine. So okay, now coming to the comparison between these two, which was the main thing I wanted to do. Merge sort is taking
Sir, the sorting orders are also found in the some built-in functions also, or every time you have to write the code of the all this sorting orders?
No. So when we actually go to the further weeks, you can just use the sort. I mean, the built-in the list dot sort or something like that, right? No problem.
Okay, it is there. We are learning here to use how to use that, right?
Yeah, exactly.
Okay.
See, the main point that's a focus why these things are important. See, learning the algorithm is very easy. There are thousands of resources and material to do that. Everywhere you will see the same thing. Important is understanding these points where I should use so 90% of the places would say insertion sort is a better sorting algorithm. Okay. Yeah, it is good because it is taking best case order in time, and my selection sort is always taking n squared time. That is fine. But what
Yeah.
happens, you really work in a system where that constraint of system number of swaps is slow, I mean, the swap operation is slower, comes into play. You would see, I mean, 20 times selection sort would perform better, not 1-2 times, 20 times I'm saying, because swapping is anyway happening in both of these algorithms. So so the main point of learning.
Sir, what makes the selection sort special in while swapping the elements in the
How many?
list?
So this also I discussed in the last session. Please check.
Okay,
Yeah.
I will have to
Yeah.
that live coding session,
No.
live
It's
session 2.
live coding is this one, right? The live.
I
Yeah.
think selection sort and swapping there.
Yeah.
Just day before I started.
Yeah.
Week 3.
So,
Yeah. First lecture.
Yeah.
week 3.
Okay, first
Okay.
lecture. Okay.
Yeah. So I think okay. Let's come back to the question of merge sort and quick sort now. Merge sort is taking n log n in both cases. Quick sort is taking n log n here and n square here. Again, if I ask you which is a good algorithm, I mean, obviously by visual inspection it states as merge sort is better because in both cases it is taking n log n. But quick sort is taking n log n here, but here it is taking n square. So why would I have why would I put myself in the danger of getting this n square in the worst possible scenario, right? So I always merge sort is better. Yeah, that is fine. But my next question is, if you have to sort in a linked list, right? So what would you do then? Just think about it. Okay, I would not tell the answer. You have to apply sorting algorithm on linked list, right?
Singly list.
Singly linked list only. Okay, let's say doubly linked list. No problem. You can travel both ways. You have a doubly linked list and you have to do sorting and you have merge sort and quick sort. Fine. Now think about which one would you do. That is your question 1, and I wouldn't discuss it now. Next thing is the merge sort operation. So this again has some important part. See, what happens in quick sort is it is taking lesser number of recursive steps, but merge sort would take more number of recursive steps. Now why? What is quick sort doing? Quick sort is dividing the array into 2 separate halves, right? And 99% of the time it would not end up in the worst case, right? The worst case is every time you pick the element which is at the last. So that would never, I mean, most of the times that would not happen. 99% of the time it wouldn't happen. So how does quick sort proceed? It's divide the array into 2 halves, into 2 parts, and proceeds further. So if let's say I divide my first half over here, first division was here, okay, an equal half. But let's say the next division was like this. Fine. Okay, so this part already got sorted. And I only have to run it for very lesser number of recursive steps over here. Right? But when you do merge sort, irrespective of the manner at what is the length of the partition, you always end up doing the same number of recursive steps, because merge sort blindly first divides the whole list into 2 equal halves every time. So the number of recursive steps and the work, and you all know I discussed in the first class that why recursion might be a problem, because you have to, recursion means basically you are putting the program, the function call into a stack, right? System stack, call stack, I discussed that. And then that call stack would be maintained and it would be popping and pushing the particular invocation of functions. Just revisit that part if you forgot. So that call stack or system stack, which was the reason for your stack overflow error, I also discussed that. So that system stack thing which happened, that is an overhead task, right? It's not something, it's done internally by the system so as to provide you the feature we call recursion. right? Or let's say function call, but specifically recursion. So that is an overhead task. Now, the more times your recursion happens, the more that overhead is, because if you every recursive call is basically doing some task in putting the
Recursive call is expensive,
function,
right?
exactly, the function call in the program stack, in the call stack. Every function call is basically doing some background task of taking the information about that function call and putting it into the relevant information, putting it into the call stack or system stack. So every function call takes that. So basically function call is costly. That's the point that you raised correctly. Function call is costly. If I can reduce the number of function calls in my code, then obviously I can gain that much improvement. So if you have a code which is kind of random, which will not end up, I mean, most of the chance you would not end up, right, when every time taking the last as the pivot element. That's a very, very, very rare case. So most of the time that would not happen. Most of the time you would be deriving this n-log n performance only, right? But Quickshot does lesser number of recursion overhead compared to merge sort. So although this is good, this seems good that in worst case it is n-log n, but in worst case it is n square. Fine, that is okay. But it's better to do Quickshot. The reason for that is it derives this, I mean, it is not having that much of internal bookkeeping work to do, because you are reducing the number of function call or recursions. Okay, so what kind of information I referred to in order to infer that Quickshot might be a good choice? The thing is system information. This is not nature of the data. Both of this, so your the system has a very slow swap operations tendency, so that is also system information. And here, Quickshot and merge sort, we saw that merge sort takes a more number of overhead because of keeping this call stack. Obviously, Quickshot also has call stack, because Quickshot also is, we are doing using recursion and function call. What I'm saying is Quickshot has lesser number of recursive calls as compared to merge sort.
What is calling the call stack?
Call stack I discussed in the first session. Please check that. Okay, ekdam first session, the first one of this term. Fine. My first session.
Okay.
Your first session.
Yeah. So I think that's the second session in the sequence. So here I'm saying about the call stack feature. So that is also system information. So that's why, in fact, that is why we call it Quickshot. And that's why otherwise there should have been any reason of calling it Quickshot. So generally implement Quickshot, not merge sort, because merge sort would take some time to do this stuff.
Sir,
Yeah.
the question you asked regarding the linked list, like which should we prefer, is the answer merge sort for that?
Why do you think so?
Sir, because in linked list, each element has information only about the next element. So in Quickshot, we take a pivot element and then we compare it with all the elements, like and
Good.
then we arrange. But
Good
in merge
thinking.
sort, we just keep on dividing. That's why I was saying.
Good thinking. The problem is when you anyway merge, remember? So the merge operation, when it happened, so let's say you have these two. Okay, let me take a proper example. Let's say 2, 14, 6. And let's say I have 3, 5, 12. Something like this. So at first comparison would be 2 and 3 in merge sort, and I would place 2.
Yes.
So what would be the next comparison?
3 and 14.
3
Yes,
and 14, right?
14,
so
yeah.
then what's happening? It's not consecutive. I am comparing
Yeah.
2 with 3 and so it's not that.
So actually, I just thought of initial step.
Nice. That's why I told nice thinking. The thing is, you have to actually think much more. I mean, merge sort is not the answer. Quickshot is also not good in linked list, not at all. But merge sort is definitely not only I would say good, it's not doable in that respect. The reason for
Yes,
that
and
is
now I get it why it's
how
not.
do you break? Merge sort's main idea is you break in 2 halves. Can you break a linked list in 2 halves? What is the mid?
No.
How can
Yeah.
it?
Yeah.
How can you calculate this?
So Quickshot also we can do. We can't do.
Exactly. That's why I said that's why it is bad. But there is a workaround for quickshot. The thing is, quickshot doesn't have this tendency of dividing in middle, right? So you can have a pointer and you can traverse it along with it, and go to a particular point and separate it out, right? But every time you have to do it in merge sort, irrespective of whether your array is close to get sorted or not. But merge sort will always travel till the middle. Okay, quickshot, whenever it is getting close to get sorted, it would not travel to middle or somewhere. It would end up very quickly. So although asymptotically it doesn't make a sense, but performance wise it would make more sense when you go for quickshot. And in general, I am telling you one thing. So let's say you have a very small length of array on which you are working, on which you are sorting, right? A very small length of array. So let's say a 4-element array. Okay. And let's say again there is another metadata, or now I'm talking about the nature of data. So how should I put it? So let's say you have some modulus function is there, some mod m function is there, some let's say n mod m, right? N mod m means what? 0 to m minus 1 are all the possible values that you can get, right? Let's say you are doing some code which is working on a list, and that list can only have values between the 0 to m minus 1. Basically, you are doing this n mod m multiple times, and whatever be the result, you are putting it into this list, and then on that list you want to do sorting. And let's say you do this for 4 times. Okay, so you do it for 4 times. So what I mean is, if this is the scenario, since you have very less element, and since there is a constraint on the values of the element, right? So just put a value. What I mean to say is, let's say this m is 4 and this is not 4, let's say 5. So you can have values 0, 1, 2, 3 and 4. These are the possible values. And here I told you have only 4 elements. So 0, let's say, then I put 2, then I say 1, and then I say 4. Now see, what I mean is, each of these value which you are putting over here, that is constrained by this number m. It cannot go beyond m. And also, not only that, there is another constraint that the list is of size 4. You don't have a lot of elements. So since there are both of these constraints, the probability that you would get sorted list, if you just make this list randomly a million times, then there would be a higher chance of getting a already sorted list, because your data is constrained. It can either have this mod m values, and also it is very less. The whole list size is less. So the 0 to only 4 elements are there. Okay, so what I mean is, let's say I have now 2 elements in a list. Okay, the same list I have only 2 elements. Obviously, the chance of this list is already this list being in sorted order is more than this list. Getting the point? Because you have only 2 elements. There is a very high chance that I get 1 and 2 here. But even if I get 1 and 2 over here, right? Then there might be it might break the pattern if I get, let's say, 4 and then let's say 3. So if the more constraint you have on your data, the lesser the size of the list, the smaller the size of the list, and let's say that the constraint on the data, what are the values present in your list. So then there is a chance of running into already sorted order list or something like that, right? But if you have large data sets on which you are working, so you would not be encountering any of this situation, most probably, maximum number of time, if the data set is very huge. Because if the data set is very huge, most of the time it wouldn't be sorted and it wouldn't be in like that format. It would be a random kind of thing, right? So in those scenarios where your data set is large, it's better to actually apply quickshot. Fine. Why I am saying this is because it would work because if you have, see, worst case of quickshot is when it is already sorted, because every time then you would pick it up and placing it at the end. Okay, and worst case of, just check out what are the worst case of quickshot. Okay, every time it is sorted and every time all the elements are same, those kind of scenario you would run into trouble with quickshot, and then this n square would come. But if you have a large data set, then this order n square, this thing happening, that every time the terminal element is given to you, that is very least. That is, every time you would get a sorted array, you are running a code on a, suppose 10,000 length list. Length of the list is 10,000, and that data is putting randomly, right? So what is the probability that you would get, if you run it for million times, what is the probability that you would get a sorted list? right? It would be very, very less. So only in that situation, when the list is already sorted, Quickshot would encounter this order n square problem. Generally, it would be n log n. So for large data set, it's generally preferred you do Quickshot. When merge sort is the only other option. I'm not saying absolutely you always do Quickshot. There are other sortings as well, but Quickshot is preferred a lot, right? I mean, it's kind of quite a good algorithm. Fine. But when you are working not on so much large data sets, right, which would it's some mediocre or some small data set, then it is better to go for merge sort. Why? Because since it is anyway less, anyway it is, I mean, let's say the data set is small, right? It wouldn't have that recursion happening a lot of times. I mean, obviously it would happen, but it would be compared to that, it would be less. So all of these are trade-offs. There is nothing absolute. So that disadvantage of merge sort kind of get under the rug in that if the data set is not very large. And at the same time, if the data set is not very large, then the thing that I told you over here, the chance of encountering sorted list is higher in small lists, right? So in that case, if you do Quickshot, you would encounter the n squared time. But in merge sort, even if there is already sorted list, it's taken log n time. So that's the whole point. You have to decide depending upon what kind of situation you are going to code, which algorithm to pick up. Fine. So I just kind of thought of discussing this. Now let us go back to any question over here. We will go back to this code now.
But anyhow, sir, merge sort is n log n is lesser, no, in the time complexity. The space matter. N log n is the lesser, no, anyhow, in any case.
Okay, yeah, that's the whole point of my discussion. You run it for 100 times. Let's say this thing will happen. N square would come into play when you have a sorted list.
Yeah, this is the only case.
I give you this is a bet I am doing with you, right? Let's say I am both of us are actually betting money. Let's bet money only, right? We are betting money, and what we are doing is, let's say you are saying that you take. I would use the random function. Okay, I'm picking up data, and I run for on a list of, let's say, size 200, and I would apply random, and I would apply and put the values 200 values in a list, right? And I tell you that only if the list is sorted, then Quickshot takes n squared time. Fine, and you run the algorithm, run this test or this experiment for, let's say, 100 times. 100 times, I would take random 200 length list and then apply Quickshot and a merge sort separately on the same list, right? I am applying Quickshot, you are applying merge sort, suppose. So if I tell you this is the experiment that we do, and I already told you merge sort would have this problem of some extra overhead, system overhead, which does not come into the asymptotic analysis part. But obviously I told you why, because recursion is a heavy task to do. And although Quickshot is also doing recursion, but merge sort has higher overhead of recursion as compared to Quickshot. So that would anyway happen, right? But in Quickshot, my recursion overhead would be less. And the only chance I would be get beaten by you is when the list is sorted. So what is the chance of that of my in 100 trials of a 200 length randomly allocated array? What is the chance of me encountering a sorted list?
1 by 200 factorial.
Can you imagine that number?
The question goes into the expectations and the probability like that.
Yeah. So that is zero. That is basically zero.
Yeah,
fine. I mean,
expectations like that.
Theoretically, it's not zero, but it's basically zero. And if I tell you the cost of recursion, that you would even encounter. I mean, in respect of recursion, I would beat you every time, even if I run it on every trial out of the 100 trials. Every time my Quickshot would do better than your merge sort. But only risk I have is if I encounter a sorted list. So obviously, asymptotically speaking, my Quickshot is at an inferior position. But in practicality, when you run code on your machine, then Quickshot is much more better as compared to merge sort, provided two things. Provided you have a lesser chance of encountering a sorted list. And when we will have lesser chance of encountering a sorted list is when there is no constraint like this modulus constraint on data, which is there in the sorted list, the data of the sorted list and the length of the sorted list. Sorry, not sorted list, I mean list, sorry. the data in the list and the length of the list. So when you have a larger list, there is a very lesser chance of encountering a sorted list. And also when you have less constraint on the data which you can put in the list, then also you have a lesser chance of getting a sorted list. So these two things, if you're, and good news is the real world, it is like that only. You would be mostly dealing with huge data, and mostly it is random. I mean, it wouldn't be something, it wouldn't be sorted out. So basically, therefore, Quickshot is a much more better algorithm as compared to merge sort when you are working on a huge data set, and basically real life data set, because in reality you would encounter such data. But again, if your data set is not that large, it is small, and it is it has lesser, I mean, the list size is small and the data has constraints, and you have some possibility of encountering sorted parts, it's better to go for merge sort, because then you can run into this order n square thing. Fine. So that was the whole idea.
Sir, but here, how will you decide? Because you are saying that if the data is like that, but you are
no, yeah, that's why I am
writing the code for a metadata, because you don't know what metadata will be.
Yeah, you would know. What I am discussing is there is no absolute solution. That's what my point is. The whole point of me discussing this thing in the live coding session is, this was very important in the respect that many books, many lectures, many places, many resources, many classes will tell you this insertion sort is good. After that, merge sort is better, and then we learn quick sort, which is better, and then we'll again learn heap sort, which is best, and then you would learn some other sort, some new advanced kind of sorting. This is the best. I am telling you that notion is totally worthless to say. Obviously, if you are comparing between, let's say, where the asymptotic complexities are exactly same in both the cases, exactly inferior in all possible cases, then you leave one of the algorithm, because if it doesn't do better in any respect, then you throw it out. But the main idea is, whenever the asymptotic complexity, I mean, the asymptotic complexity is not the only point which you should judge while thinking of which algorithm you should apply. Okay, because you have to also think on what kind of data and what is the system requirement on which I'm applying an algorithm. That is also important, because asymptotic analysis is done mostly to, I mean, in the first level of designing algorithm. But after you design the algorithm, you have to run it on the system. And when you have, let's say, two algorithms having similar asymptotic times, right? So then you have to think that, okay, even if, since most of the time these two algorithms are similar, like merge sort and quick sort, most of the time they would be n log n only. But if there is a sorted list, then quick sort goes to n square. So that is the disadvantage of quick sort. And what is the disadvantage of merge sort? It takes more recursions. I mean, the overhead for recursion in merge sort is more. So now you have to have a trade-off. Which probability is higher? Me encountering a sorted list, or the overhead that merge sort is taking? So you have to weigh the options and then think of it. But if you obviously compare between merge sort and, let's say, insertion sort, I would say obviously go for merge sort, because doesn't matter, because it is n square and n. And also there is no concept of swapping that I have told you, or any other constant that I have told you, right? So as long as, so the main idea is having this notion that this sort is bad, that sort is best. And I mean, once I learn this sort, I can apply this particular sort in all possible scenario, because that's the best one. There is nothing like best one. It depends on which kind of scenario you are writing code for. Okay, that's the main point I want all of you to understand.
Just first check whether the list is sorted or not. If it is sorted, then we have to think again, right?
Yeah, but again, yeah. So that's, you cannot always know when the list is sorted or not. So the idea is, if you see the list is small, the size is small, then the probability of that being sorted is larger.
Yeah.
Right? I give you a list size of two size list, and I give you a 2 million size list, which has higher probability of being sorted.
Probability, right? Got it.
So that's the kind of thing.
And one thing more, sir, the question will be framed in the examination point of view based on this concept. Questions will also be framed up based on this concept. This
Okay. But the thing is, we don't frame question. I mean, we don't ask you question on the basis of some real life data, let's say banking data or something like that, because anyway, this kind of course is, I mean, you have to do the code first time. So we don't go for so much practical scenario, because it would be difficult to make this kind of calls in the exam. So mostly it would be normal numbers only, so you don't have to worry about that. Whichever algorithm you feel is asymptotically faster, write that. That's it.
Yeah.
So,
Yeah.
I did your first question, and so it's passing all the test cases on Replit.
Fine, great. So let's discuss that. Okay. Oh, can you kindly say your name?
Sir, Pranjal Dubey.
Nice. Okay, Pranjal. Yeah.
So, but these linked list questions are quite confusing. Like, it's take a lot of time to figure the code out.
Why?
At least for me.
See, you had the idea in your mind, right? That what the figure looks like. And
Yeah,
then-
yes, sir, I have, but I am worried about the OPP. Like, the time is less and it takes time to me, like, to get, like,
But not only me, not only you, even we take time when we learn it first time. The thing is, these things will come with practice. So if you do practice, it would be okay. Fine.
okay, sir.
Yeah. Okay, so you did the test run, right?
Yes, sir.
Tests. Nice. Fine. So let us discuss. By the way, what is the difference between a linked list and a list? And again, when I'm saying list or array, I don't mean the Python list or array. I think those of you have gone through the lecture, you should be clear with it. Yeah. So what is the difference between a linked list and a normal array?
Sir, array, we can directly, it's of fixed length, and we can directly access an element if we know its index. But in linked list, we have to go one by one. Like,
and why is it so? Why
so
I
because
can? Yeah.
Linked list is stretchable, and each element in a list only has information of its adjacent element. It's like scattered in the memory.
So I think it's more about also contiguous memory block. In case of array, you have to get free memory blocks which are contiguous. Whereas in case of linked list,
yes, yes.
it can link together all the memory cells which may not be contiguous.
Exactly. So the main point, whatever you told, that was exactly correct. And Pranjal, whatever you told, that is also exactly correct. The thing is, that is the effect, not the cause. So the cause is this thing that in linked list, the normal linked list, right? The memory locations are separate. So if I consider a normal list or normal array, so it would be stored in memory like this. And when I say like this, what I mean is, so these are memory numbers. So any memory address, it is preceded by, I mean, when we represent it, we write the thing 0 followed by a small x, and that represents hexadecimal number. We don't have to worry about that. I'm just telling, just a kind of, it's a trivia. Any memory address is written in the form of this 0x followed by some let's say 2001, something like that. Okay. So 0x means it's a hexadecimal number, and that is how we represent memory. Memory. So what I mean is, let's say 0x2001, and suppose, let's say this is how arrays would look actually, 0x2003, something like that. And you have, let's say, you have stored A, B, E, F, like that. Fine. So this is a array, a normal array. And yeah, so basically all of these elements which you can access, so provided this array is, let's say, called ARR, right? So suppose I can write something like this: ARR of 1 is equal to what? When I print ARR of 1, that would print basically what? It would print B. And ARR of 1 basically means this memory address, 0x2002. So that means this is continuous. All the elements that you store, you see them as continuous. In the memory also they are continuous. But in a linked list, it's not like that. Although, so if if you make this picture of a linked list, so this is the single linked list, or I have A, B, and E. So these arrows are basically the pointer which is pointing to them, and this memory location might be 0x2001, and this can be 0x4003, this can be 0x9999. Okay, so these are not
scattered. It is just scattered.
It's scattered. Only thing is, we have this object, or in this representation, the arrow, and this arrow is basically pointing to, actually I should draw it in a different manner. Actually what happens is this arrow is not pointing to here, it is pointing here.
Yeah.
It is pointing to the memory address basically, and whenever you write, it goes to that memory address and finds this value. Okay, so this is how linked lists work. So since it's not continuous, you cannot directly write something like, let's say if this is the L list, you cannot write some linked list, so you cannot write L or something like this. This thing is not allowed because you don't have it in continuous memory. Right? You have to know this address. Here you already knew this address. Why you know this address? See, internally ARR always means the base address, which is basically 0x2001. This is internally always, it would always happen because it is the base address, the first address. So when I am writing ARR followed by like this any number, right? Let's say not 1, let's generalize it. I am writing, let's say M. I'm writing M. What this basically means is this information is already there because ARR, since ARR equal to this thing, the base address, it starts from 0x2001. If I just maintain this information that it starts from 0x2001, whatever may be the value of M, whenever in the program you use ARR1, ARR2, ARR3, you use it 100 times at different positions in the program, how many times you use ARR, I don't care. As long as I have this much information that the base address is 0x2001, all I have to do is 0x2001 plus whatever be the size of your data, right? Let's say this is S. Now this is a character data. So character, suppose I take 1 byte. So I would take 1 byte multiplied by what? M. Number of times I want to go. That's it. So it doesn't matter. I can have a general equation to find what would this point to. This would point me to the memory address. I just need the memory address in order to access an element. So whenever I'm writing ARR of, let's say 1, in this place I would put 1. So what it would be? 1 into 1 and plus 6, this thing, right? So I would get 2002. So this would be, when I'm writing ARR of 1, that means 0x2002. So I don't have to see what is this because it is contiguous. By using this formula I can write. But here I do not have any formula to find out the memory address. I cannot write L of 2 equal to what would be L of 2. The reason for that is this does not mean I can always write 0x2001 plus 1 into 2. This does not work, right? Because this would be basically what? 0x2003. But that's not the case. 0x2003 is not any element over here. So that's the main logic, the memory representation between a this one, right? Yeah. So between a linked list and a normal array only. Now Python has a separate implementation again that we would not discuss anyway. You can check that. If you have doubt, then we can discuss it later. So Python list work in a different manner. Do not confuse Python list with linked list. Fine. Okay, so how a queue, I mean, this is the question is basically asking you. Let me show the question at first once. So basically you have to implement a queue by using a linked list. The node of the linked list is given to you and the queue, the necessary pointers and all those things are given to you. Only have to implement the pushing into the queue and popping from the queue, which is called NQ and DQ. The NQ DQ operation code you have to write. So as Pranjal has written here over here, what are we doing over here? See, let us see at first. By the way, how many of you have doubt in this structure? I don't think you should have, because in Python you should have all have done this class and object and all those things, right? Is this thing clear? What is, how we are getting a node, how it is a queue happening?
Yes.
All these things are okay, right? Fine.
Class.
So basically what this is, that I have a class node which is representing each of these nodes. So if I have a linked list like this, right? So each of this node, what is the value? So B is the data and this is the pointer which is pointing to the memory location, right? So if I, in this you see self.data and self.next. Next is basically the pointer and data is basically that ABCD, whatever value you're storing. So this is the structure of a node. And now the next thing is I have to put all the nodes together to form a queue, right? So that is basically this Q class is doing. Okay. So Q class would have methods to put node into the this queue. So how to write it? We have enqueue. So let's see the enqueuing operation. So before analyzing the code, let us first
Can
have
you
a
draw a linked list?
Yeah. So this is how, let's say, a basic linked list would look. Okay, and whatever value you put doesn't matter, but let's say 10, 20, 30, 40. It might not be in sorted order. Okay, here we are not worrying about sorting. So what is this thing? This pointer is representing your next, right? This next. Where did it go? This one. And this next is that arrow. And now I have one. What was the name of the two pointers? Head and last. So basically, a last pointer must point over here, and head pointer must point over here.
Sir, next holds the memory address of the object.
Of the next object, next node, basically. Correct.
Okay. Okay.
Correct. Fine. So next would point to the next node in the sequence, not to the value, to the node. Okay. So this is how a basic linked list structure should look. And now let's say I ask you, you have to insert a new element in this structure so that it is a queue. What is the difference between a linked list and a queue? A linked list we can insert and delete element from a linked list in any arbitrary order. Linked list is just this physical structure. Queue is a logical idea. Linked list is a physical structure, right? Queue is a logical idea. Logical idea, why I'm saying, on this physical structure, which we call linked list, if we apply the constraint that from whichever side you enqueue the element, you cannot dequeue from that side. You have to dequeue from the other side, right? Now, many of you might have this wrong notion that dequeue can only happen from here and enqueue can only happen from the back, right? Or maybe the other way around, but it's not correct. The main idea is you can say it in that format, but what is the absolute definition of back and front? There is no absolute definition of back and front. The main idea is from whichever side you put elements, right? From the other side, you would take out element in that order, provided the order is maintained. So that's what the idea of queue is, and which is first in, first out. Okay. So now if I have to maintain this linked list in the form of a queue, and I have to insert a new element, so how would I do that? Fine. That's the main idea.
Yeah.
So where, let's say I insert. Okay. From which side you have done the insertion? Okay. Let's
Rear
go.
and front.
Okay. Great. So now let us see how to enqueue it. First of all, obviously, I have to insert a new element means what? I have to create that element because I'm inserting a new node. Let's say I'm inserting a new node over here. Okay. I'm inserting a new node over here. So I must create a new node, right? So that task is done by this line, new node equal to node of val. What is node of val? Node is that class which is creating
the data also, right?
And we are passing the val over here, the data.
Okay.
Val is the data, no, sir?
Yeah.
Yeah.
Doesn't matter whatever name you give, right? Doesn't matter.
Okay.
So
it won't create any error.
No.
Okay.
It's a parameter name. Yeah, you can use whatever. I use data, but anyway, I think val makes more sense. Value.
Doesn't matter, whatever. So by the way, again, was this concept covered in Python? I mean, it doesn't matter. There is not a lot to it, but at least theoretically in any programming language, this thing should be. These two topics was covered, actual parameter and formal parameter.
Sir, do you mean arguments and parameters?
Parameters, correct.
Yeah.
Argument is the actual value and parameter is the like just like a placeholder.
Time of defining the function.
So you all know that the name doesn't matter, right? Doesn't make any difference whatever name you give, because it's getting the value. I mean, there is another concept in some other languages which we call reference, but that also is a different thing. So yeah. Anyway, so let's coming back to over here. So first of all, we create the node, which is this line. And after that, what we are doing is, as you have already commented, nice, that if the list is empty. So the first thing is the list might be empty. That is, this is the first node that we are putting in. This can be a scenario that there is, I mean, I told that I'm creating a node over here and then I have to put it like this. But it might be the case the list doesn't exist at all. How can I know that the list is not there at all? The main condition for that is if I do not have any node over here, so my head and my tail would be pointing ahead and last, basically.
None.
They would be same and they
Both
would
will
be
be
none. Both of them would be same and both of them would be pointing to none. That is the
Yes.
main point. So I think you have used that. If the list is empty, self.head is equal to none because there is no element, right? If now again I would say one thing, it would totally work over here, but just for an advanced topic, just keep in mind it is good to check this thing while you are checking for emptiness of a list, underflow condition, because there would be a topic called circular linked list, and it's not there in our syllabus, but there even you code it in, let's say you practice some coding, there can be things like circular linked list where it is actually circular, right? So something like this. So in a circular linked list, you would have many funny situations occurring. So it might be the case sometimes that head is not pointing to none, and or head is pointing to an empty element, but tail has some elements left. That kind of situation might occur. Just for fun, I mean, just for your knowledge, I'm telling, but it's totally correct, whatever you have written. What I'm saying is it's good practice to check both of them are equal and none. So fine. So if self.head equal to none, that is okay. That is, it's empty. Then what I have to do? If there is no element at all I have to do is just create the node that I have already done and put head and last both pointing to it. So you make head also point over here and last also point over here, because both of them must point to the same location because that's the only possible location. That's what we are doing.
Sir, one doubt here.
Yeah.
So in line 17, instead of self.head, we can also check if self.tail is none.
Yeah, if self.tail is none because there is no element.
Instead of, I mean, we can do it both ways, right?
You can do it both ways, as long as your NQDQ is correct. I mean, as long as your code is correct, the whole code is correct.
Okay.
And even if writing NQ, if you have messed up something that you are not upgrading the last element, I mean the last pointer, right? So then there can be problem. If your code is correct, you can use any one of them, doesn't matter. Okay. So this is the list is empty. That is only one element I had to insert. So I created that element over here. And then since it is empty, I'm making both the pointers point to the same element, the newly created element. And now if it is not the case, if it's not empty, then what I have to do? That is basically this one, where I have to insert an element, insert the new element like this. Right? So I have to insert it like this. What I have to do? So all you have to do is simply, since you are inserting at the last, self.last.next equal to new node, because your, how can you, basically this pointer is basically your last pointer, right? Right? And sorry, not last, next pointer, right? This is your next pointer. So next pointer, all of these are next pointers. So I connect two nodes by using the next pointer. So if I have to connect this new node, I would use the next pointer. And how can I get to this position? Because last is always pointing to the last node. So I can get to 40 by using this last pointer. So if I write last, that is pointing to 40. If I write last dot next, that means basically this pointer, and that last dot next dot data, basically dot last dot next, we want to put the new node.
So 40 is pointing to the last node, last is pointing to the 40.
Last is pointing
last is pointing to 40, and now we change last to 50.
Correct. So first thing is the last dot next equal to new node. So at first I would create this link, right? Last dot next 50. This line basically is creating this arrow and joining it with 50. That's what it is. I mean this node. But what is the next task that is left? That now last is no more 40. Last has to be now moved to 50. So I have to make this thing happen and make this thing go away.
So once again, sir, here some confusion. Last.
What is the definition of last? It is always pointing to the last node in the list, right? So initially it was pointing to 40 because 40 was the last node in the list. But as soon as I wrote this line, last dot next equal to new node, that means I created a new link and I joined my new node over here. So now 50 is my last node.
Last dot next is equal to none, na, normally.
That's what I'm writing. I'm putting new node in it. Last dot next is none, but when I'm allocating new node in it, because I have to join this, right? I'm putting a new element, pushing a new element.
When
What
you
are we
put when you put new node, then the data will be there, value. Last dot next.
That is done by this constructor, right? When this new node val, constructor would put the data and create a new node. All I have to do is put the new node at its proper position.
Okay. Okay. Whenever you put the new node, then the constructor will do all these things.
Whenever I've called that, First, that's what I said. At first, this part is creating the node that I have to insert. Whatever is below this, from this to this is basically placing the newly created nodes at its proper position. Now, there can be two scenarios. If the list is empty, this is what we have to do. If the list is generally there is some element, then this is what we do. So from line 17 to line 22, it is only placing the element. Line number 15 is creating the element, creating the node. Okay. And okay, so the general case is
when the node is created by the constructor, then the two things. The next value pointer
empty
is also, and the data is also in the
Correct.
node because it is object. Is it so, no?
Correct, exactly. Yeah.
Okay.
So by default, it would be none. And now I am allocating this last dot next equal to new node. So this link is created, and this basically this structure took place because of this line, because I added it. But now next thing is I have to move the last, because last must point to always the last node of the queue. But 40 is no more the last node because I have inserted this 50 here. So I have to make last point to 50 and remove this pointer from here. So what I can do is just put last equal to new node. That's it. Make last point to new node. So now last.
This is how we add a node at the last. But how do we add any node in between the linked list?
Okay, nice. So that also we would do as a part of our next question.
Okay.
So now these two are done. Self dot last equal to new node, right? Two cases done. Next is dequeue, or basically I'm deleting element. Now, first case is obviously that can happen is there is no element again. If there is no element, then what should I delete? There is nothing to delete. So if the list is empty, again I check if head is none, then return none because I cannot delete. Fine. But if the list has, now there are again two possible scenarios for deletion. See, in insertion, I had two cases. First was list is empty. Not list, sorry, linked list, I mean. Let me write LL. Linked list is empty. And second scenario was general case that it's not empty. But in this case, in deletion, this is what NQ. And dequeue, there would be, first situation is again list is empty. Second situation is it is not general, because there can be, I am saying why it is not general. There can be three scenarios. One element is there in the list, one element in linked list, and other is general. Yeah, more than one. Now I can write general. Now why this second extra case is required over here is because since it is not addition, it's deletion. There can be a scenario when there is only one element, and if you delete that element, the list becomes empty. The list can be empty, the list can become empty, and the list might remain as, I mean, it might get a little shorter. So there can be three possible scenarios. List might be empty, list can become empty, and list will get shorter. So these three possible scenario. While NQ you have only two says, either list is empty or it is not empty, right? There can be two possible scenarios. So now, since this one element is there, how can I check one element is there now? What is the check for that?
Head and last.
Head and last equal to
okay.
Same.
Fine.
Head dot next is equal to none.
No, self dot head equal to self dot tail. Last means.
What you mean is if I write head dot next equal to none, does that
no?
No, right? It's not correct.
No.
Can you make it correct, by the way?
If head dot is not none.
Exactly.
Head
No,
dot
head
next
is
dot
head dot
next.
next is
No, not head dot next is not null.
no.
Not
Head is not equal to none.
exactly. So what you have to
Yeah,
do
yeah,
is
yeah.
add an
Head is
AND
not.
condition.
And an and means?
I'm writing pseudocode structure. Okay.
Okay. Mhm.
I mean, AND means basically AND condition, normal AND.
Okay.
Yeah. So head dot next equal to none and head not equal to none. So that means head is pointing to something, but the next element of head is none. So that means basically there is only one element in the list. So this is a second way to check whether there is one element. And the other thing that I think you have most probably have written is that head and tail are basically pointing to the same.
This is more easy.
This is easier. Head and last.
Head equal to last.
That's it.
Both condition is right. No?
Both can vary,
Both.
either or basically. So this is
Either.
also correct. This is also correct. This is a compound condition. This is a simple condition. Just visualize the structure and then it would be just a cakewalk. If you have visually thinking, then all you
How this head is equal to last is equivalent to that?
okay.
Head
Just think in terms of always think in terms of the physical structure, how it looks. Now we are trying to find out a condition for this, right?
Only
So,
one.
Only one. So if there is only one element,
Okay.
what is the definition of head and last? Head must always point to the first element. Last must always pointing to the last element.
Last element.
If both of them are pointing to the same element, then what does that mean?
Okay. Head and last, yeah, both.
Okay. In order to write code for any linked list problem, keep two things in mind. First thing is, what is the definition of head and last? And let's say you have a doubly linked list. So basically all the pointers that you have, head, last, next, previous, whatever the pointers you have, keep the definition that where should they point in your mind. The second thing that you should keep in mind is what is the current status of the physical status, the picture. How does the linked list look? That picture in your mind. If you can keep these two things in your mind, then all you have to do is just modify the pointers. That's it. So, okay, so these are the two cases. Any one code you can write and check that if the list has a single element. So if self.head is self.last, then there is a single element. Now, if you delete that element, what you have to do? You have to make head and last both none because we are deleting the only element. So that's what we are doing. Head and last is set to none. And you are returning the data since the question is asking you to return the data of the deleted node. So just keep that into some separate place and return the node.data. That's what we are doing. And then what is the general case?
So
yeah.
So in that, sir, can you show the code?
Yep.
So in that line 33, sir.
Yeah.
So when it's returning node.data.
Yeah.
So it's referring to the node class, right, sir?
No. It's referring to this variable in which I have. So wait. Is it more okay now?
But sir, the data in the DQ method, so the data is not mentioned anywhere in say.
Doesn't matter. What is this self.head doing? Where is self.head pointing? It is pointing to the first node, right? And from where do I do deletion? This is a queue, so deletion must always happen from the head, right? That I have not come to that. When I come to the general case, it would make more sense. Since it is a queue, where should the deletion happen? Insertion happened from here, right? Insert was done over at this end. So if insert is happening from this end, deletion must happen from here.
From the beginning.
From the beginning. So always my deletion would happen from the beginning. Now, if there is a single node, I have only discussed till the single node condition. If there is only a single node, then it doesn't make sense what is the beginning and what is the end, because anyway they are the same. So only that node you would remove. But if you are deleting, if there are multiple nodes and you are removing a node, then that removal must happen from the front. Now, if the removal happens from the front, right? If you are deleting the element from the front, then what you are actually doing is your head is pointing to that node which you are trying to delete. That is the first observation. You are deleting, like here you use the last pointer to insert because after the last you are inserting. Here you are deleting, and that's why you would use the head pointer, because the first one is the one, first node is the node which you are deleting. So if I put head is pointing to that node, right? And if I have to return this 10 value, so what I would do is I would make a temporary variable temp equal to head dot data. Head obviously is pointing to this node, right? Now I can write head dot data. So head dot data means this node's data. So head dot data I can put in temp and I can return that. You can also do that. But I think what you have done over here is that thing only, right? Self dot head. Okay. So you are putting the head, the whole node itself. Okay, that also is fine. So either you can put head dot data and return that, or you can, what you can do is you put the whole head thing in the temp, and since after you delete this 10 element, your head will point over here. That is, your head is now getting changed. So now you cannot gain back the value 10, right? Because you deleted it. So you should have kept it somewhere as a temporary variable earlier. So that's what you did earlier.
Shrikant, can you mute?
Yeah, fine. So
Sir, I had a doubt.
okay, let me state it in this manner. I didn't discuss the general case as of now. Might be that is an issue.
Sir, I had a issue in first, I mean, when there is one node.
Okay, tell.
When you have one node in the linked list,
Yeah.
how to represent that node? I mean, how to say that this is the only node which is left in the list?
That's what I said, right?
Sorry, you change the variable temp equals to self dot head.
That is the separate issue. You are asking that when there is one node, right?
One node, yeah.
Yeah, that's what I'm saying. When it is a one node, this condition is holding, and that means it's one element. Fine. Now the thing is, here we are asking you to return the element, return this dequeue method. If queue is empty, returns none. Otherwise, delete one element of the queue from the first point and returns the deleted element value. If I remove this thing now and returns the element value, then you do not have to do all of this. Just write self.head equal to none and write self.last equal to none. So line 31 and 32 suffices. But if you have to return the value, what you are essentially doing is you are removing this 10, right?
Yeah.
Deletion means removing this 10. So you are removing this 10. And then since you are removing this 10, what is the definition of head pointer? Head pointer always points to the first element in the list.
Element.
So that means you have to update the head pointer. Like last was pointing to 40, and then we removed this pointer and made it point to the last element, new last element. But here, same thing you have to do with head, because since you are deleting this, so all I need to do is move this head over here and remove this link which was earlier there.
Okay.
Right? That's what I have to do. But the thing is, since that's the meaning, that's what you would do in deletion. But again, the question also asked you to return whatever value you are deleting.
Okay.
Now, if you have moved your head over here, how can you return the value? Because you have already lost any contact to this 10. How will you go back to, how will you return whether what was there in 10? Whether it is 10 or 20 or whatever. Basically, what is there in this node you don't have. Because after deletion means you are basically making the head point to a next node. That's what deletion is. That's what you are doing. Simply make head equal to head next. So basically, when you see the general code, you would see the line.
But that is for general, yes?
Yeah. Does it make, when a single node is there, head and last both would point to the same node?
Yeah.
So how does it make any difference here as well? If you are deleting this head, right? What are you doing there? You are making head equal to none, and then you are making last equal to none in a single node case. Once you are executing these two steps, and let's say here 32 was there inside the value. Once these two lines of code are written, how can you get this 32? What will you return? You have to return something, right? What will you write here?
Return.
You have to actually, the thing is you should have returned 32. Now the thing is both head and last you have made them none, and that essentially means this arrow wiped over, this arrow also wiped over. Both of them are wiped over. So now how will you return the 32 value? That's the question. So this is what we are doing here. See, head is none, last is none.
Yes.
Both of these none. Now, basically, that means you have deleted the element. But now the question is also asking you return the value, return the deleted element value.
Okay.
How will you do that? Because you cannot reach this 32. You do not have any pointer pointing to this 32. What is where is this 32? You have only head, you have only last. You don't have anything else in the in your code.
Okay.
So that's why the thing is, before modifying an head and last pointers, you must keep a copy of the data which you are going to delete, so that after modifying head and last, if you need that data, you can use it.
Okay.
We are keeping in the temp.
In that temp.
That's why I modified the name to temporary. Temp.
Okay.
The
Earlier
reason
it was a node, right?
Yeah, that's just a variable.
So temp or node, these are just variable that has nothing.
Nothing
They're
to-
just for storing the value of the head position.
Yeah, exactly. Because after you modify the head itself, you will lose the contact to reach that position. So you cannot return that value because you have
Yeah.
modified head.
Yes.
And if you again think it the other way, if you return the value earlier, your code is getting finished. There is no question of modifying anything because your code would return, your function would end. So it's not that you return something first and then you do the deletion. There is no way you can do that. So you have to do the deletion first and then return the value that you deleted. But if you do the deletion first, that essentially means you are moving your head and last pointers. So if your head and last pointers are moved away, then you again lose the chance of reaching that point because you do not have any way to reach that node. So that's why you keep the value of the node at some place and then you return it. But what I'm saying is, what you could have also done is you simply self head.data. This also is fine. Simply put the data in the temporary variable and return the temporary variable as it is. So that basically means the data.
Just temp.
Just the data, because that's what is required.
Mhm.
Both of them are correct. Either you write data over here or you write data over here. It doesn't make a difference.
Okay, directly this self.head is a complete, that node is
Exactly. Self.head is basic. When I write this temp equal to self.head, this essentially means
It is taking the value of the, it is
Yeah.
taking the node and storing it into the temp.
So when we are assigning temp is equal to self.head, then the node object is referencing by the temp variable.
Exactly.
So technically it is not deleted, actually just we have
Stored.
changed the
Exactly.
Stored the value.
Exactly.
Because head also contains the value of the first node.
Exactly. But the important point is now, very good point, that we are basically, what we are doing is, we would always start our linked list or queue, whatever you want to say, from the head pointer, right? Because that's what the first node in our queue is. So if I move my head away, this essentially means my all task will start from 20, this node. So this creates the effect that my 10 node is no longer here. I mean, no longer in the list, but we have not practically deleted. I'm not putting something in the recycle bin, because this basically means I'm just moving my eyesight away. Eyesight means this head pointer. Basically, I'm not looking that 10 is still there. I'm looking away. That's what I'm doing. I'm putting head to this new position, and that's what makes this effect that 10 has gone away. But 10 has not really gone away. We have not deleted. My next question on this point is, if I do like that, if I continue doing like this, then at some time, although I would think that I have deleted and my size is still 10 or 20, let's say my whole queue size is 10. There are 10 elements in the queue. But in order to reach that 10 element, let's say I have done 1 million addition and deletion. But I would say that, okay, I have added 1 million element, but then I deleted 10 at 1 million element also. 10 less than 1 million element, let's say. Right? Try to say or think what I'm saying is, I added 1 million element, but then I use the dequeue and I deleted 10 less than 1 million element. So my list size is only 10. But the thing is, there are 10 less than 1 million element would be there, which would be actually be present like this, right? Like this 10 is actually be present, but we are not looking at it. That's what it is. I cannot access it, but it is present. So it is eating memory. It is not releasing the memory. We are not deleting it. It is still there. Temp is already pointing to this point, but it is still there. So will this cause me a problem of memory overflow or not?
Yes, sir.
Yeah, it is positive, because it will occupy some space in the memory. No?
Correct. But correct. I laid it down in this manner so that I hear this answer. The thing is, this is exactly correct what it happens. But let's say if I do not have this temp, here temp is pointing to this location. But if I do not have this temp, suppose temp is no more there, then what is your idea? Is this memory removed or what happens?
Temp is no there means temp is not referencing to that node. You are saying this thing, sir?
Exactly. But
memory will be occupied still there, but we will not be using to delete that or vacate that.
No, if we set the head to none and tail to none, then memory will be free because no variable is referencing to the object. Then garbage collector will remove that after some time.
Exactly. The thing is, head and tail has to do with
for,
this.
For that period of time when garbage collection becomes active, within that period, this memory will be occupied, right?
That is correct. That is correct.
Okay.
That is correct. But the main point that I was trying to focus on was that, as you said, that the garbage collector would remove it, but that has nothing to do with head and last, because head and last is this structure, basically this queue, and I'm talking about this node. So it had to do with that temp thing. So since temp is a pointer which is pointing to this memory location, so it wouldn't. So that's why garbage collector would know, okay, there is a variable called temp and it is referring to this memory location. That means in the program, I can again go back and write temp. And when I write, I would mean I want to use this. So garbage collector would not remove it. But as soon as I remove this temp, because see, this node can only be reached by using temp. This node cannot be reached by using head pointer or last pointer or any other pointer. Okay, this node you can only reach by using this TMP. You cannot reach this node by head or last. So I did not make head or last any change. Head or last is basically the queue structure, queue. But this node is only pointed to by the temp. So if I remove this temp, so then a garbage collector would see, okay, this is a unreferenced memory location which I can remove because no one can reach this. It is inaccessible. It is unreachable. So that's why I can remove this memory location. It is worthless. Garbage collector would do that, right? But the question is, if I run this code, since it is using this temp, right, this TMP thing, if I run this code, let's say on a 2 million size linked list, will I get memory error? Here we do not have a test case of 2 million size, but if I run this code on a 2 million size, or let's say, a very, very large data set, will I get this memory error? If I do a lot of DQ.
Without temp.
So before that, just have one doubt. When we return some function, right? So then the variables inside the function won't be accessible after that.
Very good. That's the point I was trying to come to. So thanks for that. The thing is, since whenever I'm calling a DQ function and I'm making this temp method, temp variable TMP. This TMP, this particular TMP is particular to the one-time DQ that I'm calling now. If I call DQ the next time, that TMP would be a new TMP. That would be a separate one. That has nothing to do with the previous call.
Yes, because each time it is storing the value and for deletion, and we are returning that. So
exactly,
for each node, it will be separate variable.
Yeah. So every time we are calling a function, when that function moves out of context means when it terminates, when it ends, or when it returns, whatever you want to say. So then all the memory that is relevant for that is allocated for that function, that is all the variables created inside that function body, that would be moved out. That would be the memory would be freed up.
Nullified.
So when these return statements happen, return line number 33, return happens, that essentially means this temp would be deleted, because once it is returned, my temp pointer, whatever it was here, it would get deleted. And as soon as it get deleted, garbage collector would see, okay, I cannot reach this point, I have to remove it. Okay. So that's what it is. And then let us go to the general case now, because I told anyway, general cases you delete from the front. So how would you delete it? First node equal to self.head. Again, you are doing that just to return the data. Fine. Just main line is 36 and 37. These two lines are the main line. This is returning the data. Like here you did returning the data. These two lines are returning the data.
Yeah.
Right. And these two lines are the main line, which is basically what you make self.head equal to first node dot next, right? Because you have to move the head to the next pointer. That's the main thing we discussed. Head was pointing over here, and I moved the head to this point, this 20. So move head equal to head dot next. So head equal to head dot next, and the next thing is we have to now first node dot next equal to none. That is, you basically make that value. I mean that reference pointer to none. This thing, the next this one. This thing you are making to none.
This none, red one.
Correct. But one important thing is, let's ask this question. Can I remove this line?
Which? 37.
I first dot next equal to none. I deleted this line. Basically, if I run the code, will all the test case run or will it not run?
Yes, I think it will run because self.head is now to the next is equal to first node dot next.
Why it should run? Can you repeat?
I mean, my self.head is now changed to the next node. Means if it was like this, like first the self.head was initialized to the first node. Now it has been changed to the next. Means it
That
has
is
gone
fine.
to the second node.
That is fine. This is
Yeah.
fine. All I'm
And,
saying is, yeah, this line you comment out, right? So
this line.
only this line
No,
is
sir. No.
code would not
Because
run.
we are returning first node dot data. If we have returned the head dot data, then
Why first node? What does first node dot data has to do with first node dot next? Next is anything something.
no, it will work.
Mhm.
Yeah, it will work.
It will work.
Yeah.
Sure.
Yes, I think.
What about it's the last element that we deleted?
It will work because first node is temporary. We have
Exactly. First node is a temporary thing. It doesn't matter what you do. Only you are
Okay.
using first node because you need to return this data.
Yes.
So after you return this data, this first node would anyway be
Sir,
moved away.
what
Anyway,
these
it will be.
36 and 37 lines doing?
I discussed that, right? 36 and 37.
Yeah, just
I discussed that. Huh? Okay, just check once. Okay, I told that once.
Okay.
So yeah, so that doesn't matter because even if you do not write this line anyway, this first node would be moved out. So
First node is a temporary, I think.
Yeah.
Right.
so it's passing, right? So you can remove this line. So that was your NQDQ.
Yes.
Done. Okay. Now the next thing is I would discuss the third question. The second question is inserting at a point in the middle, I think, right? What was the?
It was a double linked list.
Just a second.
Sir, I'm facing a problem in second question. I'm trying, but I'm not able to like crack it basically. Once I passed two or three cases, but not all of them.
Okay, no problem. Wait. So you might be doing some change,
Yeah,
I
sir.
mean, you're not traveling to the main point. That might be a case. Wait, just a second. Second question, has anyone else done?
So I have.
Sir, I have completed. Can you check?
All the test cases running?
Yes.
Okay, wait. Just a second. Fine. Sorry, I didn't observe your name. Can you?
Shushmita.
Okay.
Yes.
Okay. Are you talking about problem 3, Shushmita, or problem 2? No?
Problem
2,
2. 2, yes.
Okay. Okay, I can't see your problem 2 being showed over here. Wait, I'm checking. Just a second.
1 second, I am checking from my end also.
Have you submitted?
So I have completed, sir. Second question.
Okay. There's some problem on my side. Can you all resubmit once, because I see third problem in your case as well. Problem 2 I don't see. Only Pranjal problem 2 I can see.
Sir, I have resubmitted once again.
Okay, checking. Yeah, now I got. Okay, I got your code. So fine, this is Shushmita's code. It's passing all the test case. Nice. So what here we have to do is, let us go to the question. Now we got a doubly linked list over here. Now, as you can see, we have the next pointer as well as the previous pointer. 2 pointers are there. Okay. So doubly linked list and inserting basically NQ, but not Q. It's a linked list. So basically, I shouldn't say NQ. We are inserting an element at a given position, right? So let's say POS is equal to 3. So that means the third element I want to be the element where I have to insert the data value. So let's say data is 10 and POS is 3. That means the third node must have the data 10. Fine. That's what this code is asking you to do in a doubly linked list. So all you have to do is, let us go to this again and check what we would do is. So what is the structure of a doubly linked list? You would have nodes like this and arrows pointing to like this. Fine. And again, you have a head pointer, which must point to the first, and last pointer, which must point to the last node. And all the arrow right-hand side pointers, right-hand side arrows basically depict the next element and next variable, and all the left-hand side arrows depict the previous variable. So that's what it is. And now I have, let's say, position equal to 3. That means over here, let's say it was initially 10, 30, 70, 90. Let's say this was the structure, and I say that position is 3 and data is, let's say, 100. So at third position, I want to insert the data 100. So 10 would be there, 30 would be there. After that, 100 would come, and then I would have 70. Then I would have 90. And all the arrows would be like the way they should be, like this. Fine. So this is what we have to do. So how would we do that? Obviously, what is the main point of contact to inside any linked list is your head pointer, right? Because when you're starting code, you have to start it using the head pointer. So first step is you use the head pointer, and then you need to go to the position. So we have to go to the third position, right? Third position means over here. Over here. So in this place, I have to insert 100. Obviously, you see, data 100 means at first I have to call this thing node and pass 100 inside it. Basically data inside it. So this would create me a new node. So this is done. So first my new node is created. Now I have to place this new node before 70, so that that becomes my third position node. So in order to do that, what we will do is we would use the head pointer, and we will travel we would travel from the head to the point where we have to insert. Okay. Now, since it's a doubly linked list, it doesn't matter till what point you travel. But here, basically, general convention is you should travel to the node before the node where you want to insert. So if I am inserting in place of 70, which is my third position, I must go till 30. Why is it so? Because even if you go further, let's say in a doubly linked list, it doesn't matter a lot, because even if you go further, right, if you reach over here, then also you can come back. But in, let's say you are inserting in a single linked list, suppose in the middle, like this, in a single linked list you are doing, and I told you you have to insert some element over here. So you created a new node, right? Let's say you created a new node. And what you have to do is basically you have to change this pointer. This pointer you have to divert it from here to here. And the next of this one must go here. That's what basically you would do. But in order to do that, which one was the one that I told that you have to change? This link, right? This node. Which is the, I mean, to which node does this pointer belongs to? Does it belong to this one, or is this belonging to this one? Obviously, this is the next pointer for this node, right? So if you have to insert at this position a new node, you must always travel to the node which is earlier to that. So I have to start from head. Let's say you had a few more nodes there as well, and this is my head pointer. So start from head, and you would jump from head equal to head, the next of head. Then from here to here you would jump. Then from here to here you would jump. What is the meaning of jump? Jump means what? Head equal to, not head equal to, sorry. Basically, you cannot modify the head because head would point to the first pointer, first node always. So basically, you would use a temporary variable, temp equal to head, and then you would use this temporary variable, temp equal to temp dot next. So this basically means jumping. This line means jumping to the next node. Fine. So how many jumps you would make? You would make jumps as long as you till you reach this point. Soon as I mean, when you reach this point, right? When you reach this point, all you have to do is what? This is temp now because you have reached this point. Temp is actually pointing to this now. That's what your jump. You are using temp equal to temp dot next to jump, right? So now temp has reached this node. All you have to now do is temp dot next.
Where it is pointing temp dot next in the first
Head equal to temp, right? You have to reach. See, the thing is, in order to insert an element at this point, you must modify this pointer. That's what I told, right? Suppose this is my new node. That's what I told.
Yeah, that's I got. Yeah.
You got, right? So you have to modify this node to point over there.
In the beginning of the temp.
Yeah.
In the temp, we are stored because this is temporary.
Correct.
We are putting head for the connected to the next one.
Yeah. So in order to reach that head, we cannot move. If that's what I was going to.
What this temp is equal to temp dot next pointing here, physically, here first in the first node.
So obviously temp dot next is basically moving. It is jumping. So initially temp was pointing. This is line 1, right?
Now temp is head.
No, just a second. So temp is equal to head. That is fine. So temp was over here.
Yeah.
Temp was also pointing over here. But then I wrote this temp dot next. So this essentially means temp. I made a jump, and that means temp is now pointing to the next node over here.
Okay.
That's what temp dot next means. Temp equal to temp dot next. What was temp was like over here, right? So what is temp dot next? Temp dot next is this one. Now, if I'm modifying temp with temp dot next, that means temp is basically modified.
We are moving with the temp, right? By storing head to the temp. We are moving temp. Yeah.
But obviously, I didn't write the main thing because we need to move temp to this position.
Yeah.
When I want to insert at this position. But if I need to move temp to this position, I have to make one more jump and then one more jump. So this temp equal to temp dot next, which is basically jumping to the next node, must be inside a loop. Because that many times I have to make the jump in order to reach this point, right?
Temp.next, like that.
Exactly. But how many times you would write dot
Yeah,
next? Because
it is
that
not possible.
that depends on position, because every time the position would vary. That's a variable. So I have to put it in a loop, and that would run how many times? You have to do that the number of time one less than the position, right? Because if position, so I want to insert it over here. I mean, so in this diagram it wouldn't mean. What I mean is, if I want to insert in a third position in this linked list, suppose I want to insert something over here, and that means I have to reach over here. So I can start the position as a counter starting from 1, and then decrease it in each iteration of the loop. And when it would actually, sorry, not decrease, increase it. Or I can start the counter from 3 and decrease it in each iteration of the loop till it reaches 1. Right? Why not 0? Because I have to reach to the 1 node before that. That's why. So just how many times position is getting decremented, that many jumps you have to make. That's what you are essentially doing. So you put it in a loop. I would go to the code after this and you would see. So, but basically after this loop is over, by using the position as a counter variable, I would reach this node. Once I reach this node, this is the position where I have to insert. Okay, this is the position where I have to insert. So this is basically your position. Insert here. So once I reach this temp node, all I have to do is modify this next pointer to point over here, right, to the new node. So I would write temp.next. Now see, temp is over here. So temp.next equal to what?
New node.
Okay, that's fine. But if I, let's say, write new node, just see what happens. Done. What is the next task? Next task was new node, that the next pointer of new nodes must point over here, right? So that means I must write new, in order to join the list, new node.next. What should I write here now?
Temp.next.
Temp.next. What is temp.next?
No, you cannot write that.
If I write temp.next, correct. You want to say something, someone?
Can we write temp.next.next?
Next node data is lost.
Exactly.
Not possible. You cannot do that.
Yeah, if you write temp.next.next, temp is this one. Temp.
First we have to write a new node dot next is equal to
exactly
new node dot next is equal to, first we have to assign.
Exactly. First we have to, since we are losing the reference to this node, I cannot write anything over here. So I must at first do something. Let's say give some name. Let's call it some temp2.
It's like a swapping. You have to keep the variable in some kind of temporary. Once you swap, then you have to bring it back. Okay.
Yeah.
Okay. Again, temporary variable is required to here.
Yeah.
Right?
Yeah. So I would write temp2 equal to, I mean, I am having a node and then I'm writing temp.next. So this would preserve the initial value of this node, because initially what? Before I made any changes to the pointer, temp.next meant this one, this node, because this is temp.next means this node. So when I writing temp2 equal to temp.next,
new node.next is equal to temp2.
This is what I am doing basically. I made a pointer pointing to temp2. Now I am happy to make the changes to the pointer like
everybody is hearing?
Like this.
Hello.
Yeah, you are audible.
Hello.
You are audible, Srikant. Fine. So this is what I would do, and initially I wrote temp.next in temp2, temp.next equal to new node, and now new node.next equal to, since I have to now make this thing happen, and I have temp2 pointing over here, so temp2. Fine. These 3 lines I have to write. And if I go to the code, hopefully that's what it is actually. Because anyway, it's correctly written by Shushmita. So we are using, at first we are, oh, not this one. At first we are creating a new node, as I said. Then first we are using a temporary variable. And then we are using using the counter to go till the position. right? Is starting from 1. We can also, is an incremental counter. We can also do it as a decremental counter, doesn't matter. In that case, you have to check as soon as it is equal to 1. And then it's using temp while not equal to none. That is also fine. You are checking when it is not going. And then finally, the steps that I already discussed. Make new node dot next equal to temp, new node dot previous pointer I forgot, because anyway I took this example using a single list kind of concept. So same idea, same thing would happen, but again in while I'm making this pointer, next pointer, I also have to take care of the previous one like that, right? So both of this would be, you just have to write 2 more lines from what I wrote over here. Basically what I mean is you have to write new node dot previous, basically point to your temp, and this one, right? Temp2 dot previous must point to new node. Fine, that's it for a doubly linked list. So you can check that. Same thing, it has been done over here. Fine. Okay. Anybody has done the third code correctly?
So I am.
Just a second. Yeah. Sorry, can you please say who is it? Who did?
So I have done it.
Archit. Right. Archit, can you please do a resubmission once for the third problem?
I'll just do it.
Yeah.
I've resubmitted. Can you please check?
Yeah, checking. Yeah, got it. Nice. This is actually the most difficult one. As once you get the idea, it's easy. Excellent work. So let us now discuss this. Before discussing this, actually I have to give a okay. So the third question is basically asking you to create a stack using 2 queues. So can someone tell me what is the insertion deletion order followed in stack?
So last in, first out.
And what is in queue?
So for
FIFO. First in, first out.
First out. Nice. So if I have this thing, one, let's say in a queue, right? It's in a queue. First, so basically what I mean is, let's say this is a queue, and this is from where I take out elements from the front, and from here I insert elements, right? 1, 10, 4, 9. So this is my queue. And then if I ask you, then if I do multiple DQ operation, right? If I do DQ up 4 DQ operation, fine. So before that, let me ask this question. If this is the way you are seeing the queue, then which element was inserted first in this queue?
9.
1.
The 1 was inserted.
1.
Answer is 1, right? And which element would be removed at last?
9.
Yeah. And which element would be removed at first?
1.
1. So this is the idea of first in, first out. This is your first insertion, this is your first removal, right? So this is what Q is. Now, so basically if I do 4 deletion now, the order would be 1 would be deleted first, after that 10 would be deleted, after that 4, and then 9 would be deleted. This is the order of deletion. And if I do, and the order of insertion was what? Same. 1 was inserted first, then 10, then 4. This is the insertion order. But if I take it in the form of a stack, how should the stack look? If I say that the insertion order is 1, 10, 4, 9, this is the top, okay? Suppose this is my top. This is the top of the stack because this side is bottom. What should be here? What should be in this place?
So it will be reverse order.
One.
1 on the right hand side, then 10 to the left of it, then 4, then 9.
So, and what would be, so my insertion order would be insertion order is same because that's my constraint, that you insert 1, 10, 4, 9, but my deletion order
9, 4, 10, 1. 9, 4, 10, 1.
Yeah. This is the stack and queue concept. But now the question is, if I play a trick and ask you that you have 2 queues, fine, everything same, just I make a change and say you that now you have 2 queues, a new queue you have added. Only thing is this queue is basically a feeder to this queue. So whatever comes in here goes in and then goes out from here. Fine. So now what happens? Suppose 1, 10, 4, 9 is there. Okay, no problem. But I tell you that this is the question, by the way. You have been given two queues, Q1 and Q2. And insertion order is 1, 10, 4, 9. But by you, this is insertion order. This anyway would be same because I mean that's the invariant, because that's if this is the insertion order, then the deletion order reverses in stack. So insertion order is 1, 10, 4, 9. That is okay. But somehow I need to follow the rules of queue, but still have the deletion order as 9, 4, 10, 1. That's the question, right? I need to follow the rules of the queue, and I have to write a code by following the rules of the queue using 2 queues, so that even when 1, 10, 4, 9 is the insertion order, the deletion order is 9, 4, 10, 1, which is that of a stack. But you are not having a stack over here. You have to follow the rules of queue only. So how would you do that? That's the question. Okay. So how would we do that is, very simple trick. The thing is,
so we can move the element to another queue and then
exactly
add elements from that queue to the second queue, and then
go on, complete.
For D in Q1 and into in Q2.
Okay, so let me just start from the 1, 10, 4, 9 case. We would start now. Let us see what happens. So 2 queues I would maintain. This is my, suppose, Q1, and this is my Q2, and my insertion order was 1, 10, 4, 9. Right? Okay, great. And let's say this is the insertion, this is the deletion. Fine. This is, let's say, the insertion over here. Okay, doesn't matter anyway. Let's keep everything in one direction. This is the insertion over here. This is the deletion. Same thing. Basically, okay, fine. So now first one is the element. So what I would do is, I would put 1 in Q2. Okay. So, or let me check what you have done in the code, because I would take your code for example. Just a second. Q2.nq. Okay, fine. No problem. So you have taken Q2. So I would first push 1, the first element that I'm getting. So not only first element, the idea is whenever I would get a new element, right? Whenever a new insertion happens, okay. So every time I insert a new element, I insert it in the second queue. Fine. So 1 would be the first element that I insert. So 1 is inserted over here. And let's say, I mean, you insert 1 from here, that means it would be coming in front, right? Like here. So 1 would get inserted like this. So 1 is over here, done. Step 1 is insert new element in Q2. So this was my step 1. So that is done. First thing is done. Now I insert, basically the next step that you would do is
insert all the elements from the first queue to the second queue.
correct. Exactly. I would insert all the elements of the first queue, which is, I mean, in this case, see what is happening is in the first iteration, I do not have any element in the Q1. Okay. Okay, so maybe in order to explain this, I should have some elements in Q1 to explain. Let us for the sake of understanding as of now think that in Q1 is my main queue and Q2 is my second queue, right, which I would use. So let us take that already some elements are there in the Q1 which is pertinent to this order. So 1, 10, 4, 9. So let's take, according to this order, 1 is the first element in the queue, first element which was inserted, and 10 is the next element which is inserted, right? So 1 and 10. And now just assume that they are already there. Now I would insert the element 4. Fine. So how would I insert 4? How 1 and 10 got inserted? Please don't worry about that. That you would anyway understand, because in order to explain the whole algorithm, we must consider a middle step. So then it would be clear. So just consider 1 and 10 is already there in Q1. I want to insert 4. Now we are at this step. So what is the step 1? Step 1 is insert new element in Q2. So I insert 4 over here. Then next thing is what I have to do now. I see 1 and 10 are there in Q1, but my order is 1, 10 and 4. 9 has not yet come. So 1, 10 and 4. So if I have to replicate the behavior of a stack, my question is at this point when I have 1 has been inserted, 10 has been inserted, 4 has been inserted. Okay.
So the order in Q1 will be 10, 1, not 1, 10.
Sorry, I didn't get what?
So I think the order in Q1 will be 10 and then 1.
If you have, let's say,
because we are implementing a stack, right? So like in the first iteration, 1 will come. In the second iteration, 10 will be in the Q2, then 1 will come in Q2, and then Q2 will become Q1. So it will become 10, 1. And now we are adding 4. So Q1 should be 10 and 1.
Just a second. I would do from here.
So the first element we add is 1. So we will add
Okay,
Q2.
yeah. So in my when I swap, I actually think in terms of Q2 to be the outing element. No problem. You have done it using 1 as the outing element. Okay.
Yes, sir.
No problem. Okay. So fine. But then I have to explain it.
Sir, it's fine. Till now it's clear.
Okay. So the thing is, okay, you consider now that whenever I would, so before why 10 and 1 this thing is coming is, I want to say that whenever you are, let's say, this whole thing should act as a stack, right? That's our aim. That's done. Fine. Okay. This must act as a stack. And now next is if this should work like a stack, I would do that by using this Q1 and Q2, but my main, I mean, whenever I'm dequeuing, right, basically the pop operation of the stack, whenever the stack would pop out, that would happen, assume as of now, that thing I can do that from Q2 as well, I can do that from Q1 as well, but whichever I choose, I have to stick to that depending upon the push operation. I know things are not getting clear, but when you fix one thing and proceed, it would get clear. I would discuss. Thing is, as of now, just assume that Q1 is the queue from which my data would move out, right? I told you 1 and 10 was there in Q1. That means 4 is there in Q2. So that means you can move data out from either Q1 and Q2. I am now choosing that whenever stack pop operation I have to replicate, that I would do it from Q1. So basically, whenever I'm popping the pop operation of stack that I will write, I would move, I would remove element from Q1, which would correspond to that pop operation. Okay. So if that is the case, then Q1 data should be in a format that should replicate the behavior of stack. Now, if 11049 is my insertion order, forget 9 has yet not been inserted. 110 and 4 has been inserted. Now, if 110 and 4 is my order of insertion, and if Q1 is acting like the stack, then I must keep elements in Q1 in such a manner so that when I pop, right, that should replicate the behavior of stack. Now, as of now, I am iterating through the step of 4. So I have not yet reached the conclusion of 4, but 1 and 10 has already been inserted. So 1 and 10 should be there in the format of a stack. Okay. So since 10 is the last element, 10 is after 1, so 10 must be in front, because that's how stack should behave. So 10 should be there, 1 should be there. I'm repeating again. My assumption is that I would, whenever I'm popping from the stack's pop operation would remove element from Q1, not Q2. The element in pop operation of stack would remove element from Q1. If that is the case, the element inside Q1 should be in the format of the stack. Now, if I consider 1 and 10 are the elements in Q1, since 1 is inserted first, therefore 1 should be, towards here, at the right end. And 10 should be at the front end, because removal of element in this Q1 happens from this end. And stack must take care that whatever element got inserted later, that must get inserted, that must get removed first. So since 10 get inserted after 1, 10 must get removed first. Fine. So it should be 10 and 1. How it is happening 10 and 1, I would discuss. But assume Q1 is acting like the stack as of now, and that's why 10 and 1 should be the order in Q1. Now we will check how Q1 is actually getting this order. So 4 is inserted, and step 1 is insert the new element in Q2, which is I have inserted the new element 4 in Q2. Okay. Now the next thing that I have to take care is that I must insert 4 in Q1 in such a manner so that it holds the property of the stack. That means what? I must insert 4 in such a place so that whenever a deletion happens, 4 gets deleted. That means if I have to replicate the behavior of stack, I have to insert 4 at the front. Ideally, that's the idea, because 4 happened, 4 got inserted after 1 and 10. So, and I told you Q1 is the one from where I would delete. The stack's pop operation would happen on Q1. So if after inserting 4, the immediately next operation, if I do pop, so that must pop 4 from the stack. So 4 must come in front over here. But I told you we have to follow the rules of Q. And Q says you cannot insert 4 from here, because 4 must be inserted from the rear end. So 4 should be inserted over here. But again, if I do that, then again, if I just after inserting 4, if I write pop, so then pop would actually pop out 10. But that shouldn't have been the case, because 4 must get popped out, because 4 got inserted after 10. So if I want to replicate the behavior of stack, then I'm getting this problem that 4 must be kept in front, but I cannot do that because Q is constraining me to insert 4 from this end. I must insert 4 from the rear end. Okay, so this is the problem. Now how to solve this problem? The thing is, what we would do is 4 must be at the front end, right? That's our main concern. You see, Q2 has 4 over here in the front end. So if I just write a pop operation, so Q2 would, on Q2, so then 4 would be popped out. That's fine. Only thing that we now need to do is, I need to take these 2 elements which are in Q1, and I need to follow the popping rule of Q. That is, I pop 10 first and then 1, not popping, the dequeuing rule of Q, which is pop dequeue 10 first and dequeue 1 then. and in this order, I insert them over here. So what would happen? Because this is dequeuing from front, so 10 got dequeued, enqueuing from back. That's the rule of stack queue, right? So I'm enqueuing from this end in the new queue and dequeuing from the front end of the old queue. So I'm first dequeue 10 and then enqueue 10. So 4, 10, and then 1. Now you see, now if I want to have the output of output replicate the like stack, then Q2 is just like becoming the stack. Initially Q1, we assumed that Q1 is the stack because 10 and 1 should be the order. But now I think that, okay, Q2 is now looking like a stack because 1, 10, and 4 was the order of insertion, and see 4, 10, and 1 is the order of deletion if I start dequeuing from the front by following Q's rule. Okay, so the Q2 is like acting like the stack. But I told you, so what can we do now? So what is the solution to this? Initially I thought Q1 is the acting like the stack, but now I see Q2 is acting like the stack. What is actually happening is every time we repeat this step, right? Every time we repeat this step, Q1 and Q2 will alternate. Let us take one more example. So this is the current state, 4, 10, and 1. Fine. Now if I insert 9, this is the next example, right? Let's 9 is the term. I told you insert new element in Q2. If you insert the new element 9 in Q2, that would be inserted from the rear end. That is, it would be here. But is it correct? Is it now representing stack anymore? Is Q2 representing stack anymore? No, because 9 is the last element inserted, but it would not be the element moved out, because now the element that would be moved out first is 4, because it is in front of the queue. But ideally, if it would have been stack after insertion of 9, 9 should have been in the front. The same problem that we faced earlier. So basically, we would not insert 9 over here. Rather, we would again use this empty queue left over here as to insert 9. So I would insert 9 in the front. And would repeat the same task again, because now I have 9 in the front, and then if I pop, then 9 would be moved out from here and it would act like a stack. So all I have to do is move the elements from here, and just like the one I did, you insert it from there. So dequeuing from front end 4, enqueuing from the back end 4. Okay, dequeuing from front end 10. From here you dequeue the front end and enqueue at the back end 10. Likewise 1. Now you again see this is now acting like a stack, and this got empty. So at every step, Q1 and Q2 would be alternating the alternating their behavior of stack. In one iteration, Q1 would be my stack. In the next iteration, Q2 would be the stack. Fine. So how to actually gain this behavior is, what I'm doing is, every time I am doing this, this function is being called, this dequeue operation is, push operation is happening. I want to push a new element in the stack. That basically means I am pushing the element within these two queues. I would use one of the queue which is empty to push the new element, and I would dequeue all the element from the other queue and enqueue it in the new queue. That's the basic task. And in the next iteration, the behavior swaps. That basically means I have to swap the two queues. I have to make Q1 to be Q2 and Q2 to be Q1. Okay, I'm again repeating. Step 1 is insert new element in Q2, suppose. Step 2 is dequeue all elements from Q1 and enqueue them in Q2. Step 3 is, once that is done, you swap, because now your stack behavior has changed. So swap Q1 and Q2, because it is alternating between every call. So once the push is happening, in the next call, Q2 would perform like the stack. And in the first call, let's say Q1 was performing like the stack. So swap Q1 and Q2. Okay, so now if you go to the code, so these are the steps, 3 steps. Insert new element in Q2. If you say that why can't I insert in Q1, you can definitely do that. Doesn't matter. The name doesn't matter, because this is where you are swapping. Only thing that matters is you have to again take care of from which one you pop. So if you write insert new element in Q1 as the step 1, then everything else would remain same over here, doesn't matter. But when you write this is for push, right? This is push operation. This whole thing is we are discussing the push operation, how you are pushing element. But when you would write the pop operation, then if you write Q1 over here, then you have to pop from the Q2. And if you write Q2 over here, then you have to pop from Q1. That's the difference. These lines would remain same. Now, if I go to the code, it would make more sense now. What we are trying to do, just keep these three things in mind. Insert new element in a queue, dequeue all other element from the other queue and enqueue them in the new queue, and then swap the two queues. These are the 3 steps, and I discussed it over here with the example. So now let's see this code. This is the push operation that we are discussing now, right? So first thing is what? Q2.enqueue data, the thing that I was telling you, first enqueue in any one of the queues. Here we are choosing Q2 as the example. And then what do? So Q2 was the initial list. So initially over here, basically what this means is your Q2 was empty at this point. And Q1 had elements. Okay. Now here what you do is, I told you once you insert the new element, the only new element, right? Every time you would insert the new element in the empty queue, which is Q2 over here. So you do that. That is done. Next is you dequeue all the element in the other queue, which is Q1, and enqueue them in Q2. Put it from the back. Now after that is you swap. So you dequeue all from Q1, enqueue them in Q2. That's what you are doing. Dequeue from Q1, enqueue each of the element in Q2, and after that you will swap. So this is basically a swapping that you are doing. Q2 would become Q1, Q1 would become Q2, and obviously you have the size parameter over here, so you increase the size by 1 because this is a push operation, so the size should increase. So that's what we are doing. Now if we maintain this thing, I told you, if you are doing this first operation as Q2, right, you could have also written over here Q1. I mean, replace Q2 with Q1 in this whole code. You can do that. Wherever Q1 is written, you can replace that with Q2. Only thing that you have to take care of in while you writing the pop operation. So pop is also discussed over here. First thing is we are using the empty function to check whether it is empty. If it is empty, you are writing stack.empty. Stack is empty, sorry. If it is not empty, then what you have to do? First thing is size you reduce by 1, because anyway it is like here you increased by 1 in push, you reduce by 1 in size, in pop. And only statement which is one line statement for the pop operation, you are Q1.dequeue. That's what I told. Remember that I am treating that Q1 is the acting like the stack, right? So Q1.dequeue, because if you write dequeue from here, it would dequeue. And this is, you see that this is the stack order. Deleting order in stack was 9 front. So here also although you are deleting from Q, and that means this is the front element. So FIFO is holding, but still 9 would get deleted because 9 is also the order for stack pop. Okay. So yeah, only thing is if you write over here Q1, right, you can change all the Q1 and Q2 swap in place of Q1 and Q2 over here. Only thing that you have to change is over here you have to write Q2. You cannot write Q1. Right? If you do that, then that's it. So push and pop. The main idea is you are generating the LIFO order by using 2 FIFO order in the reverse direction. That's it. Fine. It's better. I explained whatever is there, and the code is also nicely written. The one point is, I would request all of you to think it on your own terms. When you think it, I mean, just by taking some example, it would make more sense that how these steps are relevant. Okay. Although I tried to discuss how it is getting relevant. So yeah. Yeah. Any doubts in this, or else we have done all our codes today? No doubt, right? Fine. Okay, then. By then, we will meet you in the next session. And by the way, next I think week 4 is graph. So introduction to graphs. So from here the difficulty level would increase a bit more. Week 4, 5 would be a little bit difficult, but again, I mean, once you are okay with graphs, then again it would actually loosen up. Fine. Thank you all.
Thank you, sir.
Thank you, sir.
Thank you, sir.